All right, so I'm going to go ahead and start. So it says model an area of land as a two-dimensional grid of integers where each integer represents elevation of that portion of land. Water can only flow from a grid square of higher elevation to lower elevation. So the number at every location in the matrix represents a elevation. So we can go from higher elevation to lower elevation in four directions: north, south, east, west. Then complete the recursive function that takes in a 2D array of integers storing the elevation levels, and then another one or zero, that has that represents whether or not it's been flooded. So one is flooded, zero not flooded, as well as the current row and column that was just flooded and marks the current and all subsequent squares. Okay, so pretty much it's like you're gonna start at a certain point, right? So this right here, these are going to be two indexes that are going to be within the bounds of, like, it's going to be greater than or equal to 0 and less than 10, and then the column is going to be greater than or equal to 0 and less than 12. Sorry, so it's going to be from 0 to 11, and this is going to be 0 to 9. So you're just trying to flow as far as you can while your neighbor is like a greater or a lower elevation. So let me draw it out. So let's say we have, okay, I gotta zoom in for this one. So let's say we have, you can think of it like a mountain, right? So this is your mountain, and then this is like the valley in the mountain, right? So, and this right here. So let's say the location of this mountain is right in the middle. So let's say this is going to be 5, right? So the peak of this is 5. And to make it a little different, let's say this one's going to be like 3. And this is going to be 2. So pretty much, if you try to flood from this point, you like put a bucket of water. If it can, it'll end up going this way. But in this picture, we know for sure we can go this way, because the whole idea is you can go from a location of higher elevation to an area of lower elevation. So I guess you can put 2 really anywhere here. So like, since we're checking up, down, left, and right, it doesn't really matter which location, like where this one is, as long as 5 is greater than whatever is like your neighbor, up, down, left, or right, then it'll flood towards that direction. So you can say that this is 2, and then let's say you have 3 anywhere that's directly next to 2. So let's say we have it right here. It could also be here, it'll look the same, but the general idea is that from 5, you're gonna pour your water, right? And you're gonna mark it flooded in here. So this is gonna be flooded. So let's just mark it flooded, like by turning it blue. We're gonna have another matrix for this, the flooded matrix that they tell you about, but let's just visualize like this. And you're gonna go in this direction and flood this square. But the problem is, since this square is 2, you're not gonna necessarily go towards 3, because you're kind of like simulating water falling down by gravity, not like going upwards. So it would just bottom out and stay in this range, and it won't end up covering or flooding 3. So that's like the general idea. And I'm sure you guys are familiar with flood fill. It's kind of something that they touch upon very lightly in CS1, maybe once or twice you actually use it if you ever got a quiz question on it. But the general idea is, it's kind of like Microsoft Paint. So let me just go to Microsoft Paint real quick, so I can show you guys what I mean by that. So let's say I draw a square, right? So flood fill, it pretty much starts at a location. So let's say I flood it at this dot right here. It's going to, by some criteria, keep searching and keep going until it floods an entire region, until there's some sort of base case. So in this example, you can say the base case is it hit one of these black edges, right? So let's say I flood this right here with red. So now it completely expands, goes every little pixel until it covers the whole thing, and it can't go any further. So this is essentially what the flood flow algorithm does. And let's say we have a little hole in our thing, then that's where the whole canvas just turns red. So that's flood fill right there and how it kind of works. So it's just going to keep on infinitely going until it covers all possible areas that qualify a condition. The condition in the one that we are looking at is while we have like a white area. So I think if I cover this as red and then I cover it as green, yeah. So it just takes whatever color you clicked on and then it'll keep going, covering that while it can keep going to red, red, red until it just doesn't find the red anymore. So that's kind of the idea of this. In our case, it's going to be flooding, flooding, flooding until it can't flood anymore. So I hope that makes sense as to what it is. So in terms of the actual code of how to work, let me just copy this over real quick. I should have done this earlier, but forgot to. Okay, so we're going to have a base case. And let's just think of our base cases. So if we think about the same type of thing, we have a sort of border that we cannot go past by. So in terms of our border, we might have multiple ways to quantify, like if we're at a border. So for example, let me go to the Microsoft whiteboard. If we ever go past any of these lines, these are the dimensions of the matrix, right? So if we go past past any of these two lines, oh, see you guys saying, oh shoots, oh god, my bad. I was going too slow, my bad, my bad. Okay. Okay, so what I was saying is that you cannot go outside of the grid in this sense. So you're gonna have to have some sort of base case to check if you're in bounds, which is why they provide you this right here. So they provide you this inbounds function to say if you're going out of bounds, because the whole idea is if you go like -1 index, then you can't index into this without seg faulting. So you want to protect yourself from doing that. So that's one of your base cases, the edges. And another one is you don't want to go to a place that's of greater elevation. So let's just mark our base cases. So we have one inbounds is a base case. Inbounds. Our second base case is going to be if it's already flooded, so if flooded. And then our third is kind of like where we don't want to end up going to if we don't have to, which is going to be an area of higher or equal elevation. Notice how it only said of greater elevation to lower elevation, not equal. So we don't want to go if greater or equal elevation. So these are going to be our three base cases, but we might not be able to fit them all here. So let's think about how we can do that. So, okay, let me just write this out. Okay. So what I'm going to end up doing is, since we start off at a certain location, the only way we can start at a location if it's valid. So the very initial location is going to end up being like not flooded or not visited, because if not, then we would have never even made an initial function call to go there, if that makes sense. So like one thing I always tell people when they're like studying for foundation is like, you got to think first, sounds kind of dumb, but what came first, the chicken or the egg? Like you cannot make a function call to something that is flooded when your criteria is that it's not flooded and that it's not inbound. So right here, we're not going to necessarily be checking like if this is going to be flooded or not. So let's just do this. If inbounds, we can do any of these and any of these right here. So let's do inbounds. So let's do row and column. So what we're going to do is if it's not inbound. So if it's not inbounds, we don't want to go there. We're going to go out of sight of the grid. Then flood fill, classic thing that you have to do is you have to mark where you are. So let's say we are at this point right here. Let's say we're right here like we were before. We have to mark. So this is our elevation grid. So we have 2 and then 3. Then we have the flooded grid. So this is all going to start off at 0. Let's just assume we haven't gone to anything yet. And this is where we're going to start off at. So if we're right here, we're going to start off not flooded, because if not, then we would not start off here. And once we're actually here, once we make a function call to get there, we're going to mark it visited, which is kind of like saying it's flooded, because the only way we're visiting is to flood something. And the whole idea of doing that is when you end up recursing to another square, if you don't mark this as flooded before you go, so what's going to happen is going to go this way, then you're going to see your neighbors and you're going to say, oh, I can check all these directions. So we know we're not going to go this direction. We can end up going this direction, but let's say first, instead of checking those two, we end up, wait, what do you guys comment? Oh, do we always start in the middle? No, we don't always start in the middle. Okay, so what I was saying is that, let's say instead of checking these three directions, let's say we checked this direction first. So what's going to happen is we're going to see, oh, we're not visited, or we're not flooded. So let's keep going that way. Then you're going to come back here. Oh, we're not flooded. We're not flooded. So it's just going to literally just end up recursing infinitely back and forth, back and forth. And that's where you hit a seg fault. Yeah, exactly. So that's one of the key things with flood fill. Like that's, if you miss that, like it's probably going to give you a decent chunk of points off. So that's one of those things. So that's why you mark first, okay, I've been here. So that then later on, when you go to somewhere that you could end up back at where you just were, then you're like, oh, okay, I can't go there. So now you're going to be here. And then now from here, if you try to check back, you're going to be like, oh, okay, I can't go there because I just was there and I flooded it. So that's the whole point of this right here. So we're just going to mark where we are, which is our current location. So that's going to be row and column. And we can just mark this as 1. It's 1 and 0. And then we have this for loop, right? So it's up to 4, and there's 4 directions. So if we think about the rows, this is our row axis. So this right here is our row axis. This is our column axis, right? So first, we're just going to iterate through them, and we're going to say, okay, so what if I go back 1 row? So back is actually up. I know it's like confusing, but back is up. And then in another scenario, we're going to say, okay, what if we just go -1 in column? So -1 in column, instead of being like back upwards, it's actually back towards the left. If you go +1 in column in column, you're going to end up going to the right. And if you go +1 in row, you're going to end up going down. So you're going to iterate through those. And what do you guys think that we have to add? We have to add where we currently are, because that's the only information we have as to where we can travel to. Based on our current location, we can make 1 step in any direction. So we have to calculate, like, what exactly are we going to end up doing? So we're going to take the current row plus where we want to end up going. So that's going to be dr of I. So that's going to give us our next location based on whatever like movement we're going to make at the current iteration. So dc of I. So that's cool. Now we have our next location. So at this point, pretty much what we have is, let's say we're right here. We're like, oh, let's consider going here. So we've only calculated the location of this box. We haven't done anything else at this point. And yeah, marking this 1. And now we're gonna try to invalidate and kind of like protect ourselves against where we kind of want to go. So we're going to steer ourselves now. So pretty much we're going to do any invalidation cases here. What I mean by invalidation case is like, I'm going to say, okay, so I'm not going to recurse, which is what we're going to end up doing if whatever this is true. I'm not going to recurse if this, and this is true, because we don't want to go that way. So we only want to go if multiple conditions are true. So let's think about our base cases. You use base cases to say where you want to stop at, right? So what if we just think about the opposite of our base cases? Then that'll tell you where you want to keep going. So if you just take the opposite, so you can technically say this is like not in bounds. I meant to say not in bounds. So not in bounds. So we want to keep going if we are inbounds. We want to keep going if we're not flooded. Not flooded. And we want to keep going if where we are is a greater elevation than where we're going or where we're looking to go. So that's going to be how we're going to think about it. So as I said, we're going to look at our base cases. Just have 3 little lines here. So, and these are all cases that we want to all be true, because if one of them is true, then we're not going there, you know. All these things have to be true. So 1, let's check if the new location that we've established, is it a valid location within our major? If not, then we don't want to go there. Next C. So if it's inbounds, and so by checking if we're inbounds, now we can use our indexing, because let's say, for example, we did something like flooded next R next column. If we did this first before checking if these indexes, this location is inbounds, then we can segfault. It could happen, it could not, but chances are it probably will. So that's why you want to check, okay, are these indexes good to index into? If so, then let's consider like actually using them to invalidate stuff. And flooded is not true. So if we're not flooded, and the final condition is if the grid, so grid is representing the elevations at every location that we're at. If grid of where we currently are, so that's row column, that's what we're in the recursive call. If it is greater than the elevation at grid of next R next column, and again, we can use this because we validated that this location is good to index into and even go to. So these are all the conditions. So now we're pretty much going to end up invalidating cases that we don't want to go to. And technically, I don't really get why they added this, because this handles it, assuming you're only going to start off at a valid location. So I don't really get why they added this. This could have been really, it could have been this base case. It could have also been a different base case, like this one and whatever. But I just put this one in because it's like the most general case, you know. So that's why I did it like that. And yeah, let's see what the answer is. And funny enough, I was doing this question once with a friend of mine, like when we were studying for the last foundation, and they didn't check stuff. Like this question is literally, like the answer is literally wrong. Because think about it. They say here, okay, you're not inbounds. So that's good, right? Row, column, and then 1. That's fine. So we mark where we are before we go on. We calculate the row, calculate the column, and then it says here, if grid of next row is less than grid of where, or sorry, if grid of where we're going is less than grid of where we're at. So that's fine, right? But the thing is, they don't even check if it's flooded. So anywhere. So their code would actually not work. So I found that kind of cool. I remember doing this one once, and yeah, they don't check ever if it's flooded or not, which doesn't make sense, because if it's not flooded, then you don't want to go there, you know? So yeah, just an interesting fact about this question, but this is the real answer right here. This is what you would actually end up doing. So yeah, I'll keep this code here, but let's move on to the other question. You guys have any questions about that? +1 in a row is down. Yeah, exactly. So inbounds is true. It returns anything greater than 0. Yeah, exactly. So pretty much this statement here, it's a huge like Boolean statement. So it's pretty much like chaining what you get. So let's say you have row is 0 and then column is 3. Really what it would return is, let's check if this is, let's do like 13. So that's going to be out of bounds on one of them. So it's just going to be like row is greater than 0. So that's true. And row is less than num row, which 0 is less than the number of rows. So that's good. And then if the column is greater than or equal to 0, this is greater than or equal to 0. So that's true. And then you're going to say column is less than num columns. Num column is 12, but this is 13. So that would be false. So you're just gonna take like the result of this. So true, 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 like all ands, it's just gonna end up being false ultimately. So yeah, it just returns false. And remember in C, true is 1, false is 0. So you can just check 1 or 0.
That's
It
what I
won't
was
do
gonna.
anything.
That's what I was gonna ask. Okay.
Mhm. So yeah, anyway, that's that. So let's go on the next question. Okay, so I'll let you guys read it and we'll come back at 7:30. Okay, so 7:30. So let's see. So consider the problem of transforming a positive integer x into a positive integer y when there's only two operations you are allowed to do. So that's adding 1 and then or multiplying the current number by 2. Write a recursive function that returns a minimum steps to transfer x to y. If x is greater than y, return big number to indicate that no solution exists. So let's see, if 13 or if x equals 13 and y equals 28, the correct response would be 2. So you add 1 and then times 2. So that's just 2 steps. Okay, and they also provide a min function. So they say also that they want to test recursive thinking. So don't try to just do like some simple math to try to get the answer. They want you to do it recursively to find the minimum answer. So let's think about this example that they give you. So let's say they give you some other numbers. So let's say 6 and what else is there? 21. Let's say 21. So this is your x and this is your y, okay? So your entire goal is to transform x into y. So there's two things you can do. So you can either add 1 or you can either multiply by 2. So let's think about the quickest way to do this. And obviously when it comes to recursion, it's not going to directly go to the quickest way. It will end up doing whatever you do in the code and then ultimately have its answer. So let's go here. Goal is 21. So we're going to start at 6, right? So let's think about it kind of like a tree, because we're going to have two directions that we're going to be able to transform at every given step. So we either add 1 or we either times 2. So in regular recursive manner, we're not going to go to times 2 unless we're done with this whole process of adding 1 and whatever comes under this. So I'll show you what I mean by that. So let's just go down the +1 route. So if we go +1, we're going to end up at 7. Then we're going to end up going 8, 9. So we're just going to keep on going. And I guess you guys are probably going to see what's up now. We're going to keep on doing this until we hit 21, right? Eventually. So I'm just going to do like eventually we hit 21. So it's literally just going to do 21 minus 6. So that's going to be,
scenario.
yeah. So this is worst case scenario. So this is like how bad it can be. And of course, if you think about it, as you approach, this is gonna sound kind of like calc, but like as you approach 21, like the number is gonna, like whenever you do your multiplication, they're actually gonna get more and more useless to do, because the bigger and bigger your number is, doing times 2, it might actually shoot you over the number. So let's say we were at 20 right here. You do +1, then if you do times 2, you're going to be way over. So you're going to have a lot of stuff that you're going to end up doing unnecessarily. So if you're thinking of just like the quickest way and like logically to end up doing this, you're probably going to want to do the times 2 first, if anything. Like just, you don't have to do it in code, but just thinking about it, it's better to make the jumps on the exam. So on the exam, you don't have all the time in the world to be doing this, right? So you're going to want to choose the quickest way. So let's think about it. Instead of doing +1, what if we do +2, or sorry, times 2 every time? So 12. Okay. Now we're going to do times 2, 24. We're going to say, oh, this is greater than 21. So we just read the instructions. If x is greater than y, return big number, or no solution is what they called it. Right? So that's pretty much invalidating this, because since we're finding the minimum, if we take such a big number, the whole idea is that there's not going to be any number that's going to be greater than this. Like, because yeah, they say assume the numbers are really small and whatever. So ultimately, this is going to be times 2, and it's going to return big number. Okay, so now from this point, we're still in this recursive tree, right? So we're still currently in this recursive tree. So let me draw that out. And now we're going to end up going on another path, which is going to be +1, right? So let's do 13. And now we're going to end up following the same steps. We're always going to go times 2 first. And again, it's also going to be a little redundant at this point, but I would argue this is nicer and easier and faster to think about than on the test. So let's think about it. Then we can end up doing 14. And yeah, you're pretty much going to end up after this point, keeping on doing a bunch of operations. But if we think about the quickest way to do it, let's see. So it's probably going to end up going to 21. So plus 7. So 7 to 3. So that's about 10. Let's see another example. If we do +1, and then +1, +1, and I'm ignoring all these times 2 right now, but I'm just going to show you a quick example. So yeah, let's keep going. So let's do +1, then 10. And now at this point, let's say, what if at this point we're going to end up doing times 2, right? So I ignored all these because, like, obviously they're going to have their own like +1 chain that goes big. And also, if you do like 7 times 2, it's going to give you 14. And there's no point in doing times 2 on those. So in terms of doing it the quickest, now here you're going to see, oh, 20. And then you're going to do +1, and that'll hit 21. So in this right here, we ended up doing 7, then 8, 9, 10 operation. But here we ended up doing 1, 2, 3, 4, 5, 6, 7. So just out of that, that beats it. So that's the entire idea. So you're going to end up summing all of these like +1, not necessarily the +1 itself, but the fact that you ended up doing an operation, an operation, an operation, and so on. So let me see what the chat is saying. So that makes sense. Yeah, exactly. So look, in the exam, you're trying to go as quick as possible. You don't have time to be like doing this whole thing right here. Like that's why even and I'm not even doing that. So you shouldn't either. So let's get to the code. Okay, I almost caught myself. Look at that. I almost showed it, but all right. So let's think about it. Base case is if x is greater than y, we're going to end up doing is return no solution. Because again, we're trying to minimize, so that's why we throw out this big number if we get an invalid or not like not what we're looking for, you know. Because think about it, if we're only adding and we're only multiplying on positive number, it'll only ever go bigger. So you're literally going to infinitely never stop if you don't have this base case. Because then as you grow past that number, you're never going to go back to it. So it's the whole idea. So now at this point, we can store the recursive call. Let's do +1 equals. So we're going to add 1 here, but this is not necessarily the whole thing of adding +1 to the number. It's just saying, okay, we're going to do one step, which is adding 1. That's the step we're going to take. So we're going to do min steps of x + 1 and then y. And then next one we're going to do is times 2, which is going to be 1 step, because that's one operation that we're going to do now. And then we're going to do x times 2 of y. So this is where we're at right now. And now what we can do is say if +1 is greater than times 2, return times 2, else, or you don't even need to do an else, but yeah, you can just, I'll just write it so it's simpler to see. Else return +1. So we're pretty much taking the minimum every single time until we combine all of our answers together, and then we get the ultimate solution, like the final solution. So let me see what you guys are saying. Could you use the min function? Oh yeah, my bad. I forgot about that. So you could use the min function, but let's see. You could, but
Zain is too cool for that.
yeah, you can say that.
But-
So
Okay. I was only asking that because like if you don't use it, you don't get points off. Like it doesn't matter.
No. It doesn't matter.
Oh,
It really
okay.
doesn't.
Okay.
Yeah, they're just saying like if you feel like using it, you could. Because like the thing is, people code it differently. Like if it was me doing it, I would have coded different than what I did here. But like I try to tailor it so like everyone can understand, if that makes sense. So like, this is like the simplest way, because what you would have done would be like int answer, or like int minimum steps equals minimum of +1 times 2, and then at this point, then you can just return minimum steps, which is the same thing that I had before, or you don't even have to make this variable. You could just do this, but I was just trying to make it like easy so everyone can understand, because this might look a little confusing to some people.
Okay.
You know?
Yeah.
Yeah, like on another way, you know, like it's like this, but that's even more confusing. You know what I'm saying? So like
That's the way I thought to do it with the return +1.
yeah. Look,
Like
look.
if you're counting
If that's
the
good
height
for
of the
you,
tree.
you would do that. Like
Oh, okay.
since I like gotta, you know, make sure everyone's good, I just do it the easiest, simplest way to get it. You know?
Oh no. Okay. Mhm.
Yeah, that's that. So let's see what they got. So if it is equal, oh, I forgot if it's equal. My bad. Okay, that's equal. Return 0. Yeah. So then you're done at that point. So it's just like when we hit right here. Once we actually ended up hitting this, then to get from 21 to 21, there's no operation. So you just base case out at 0. So then you just do 0 plus, oh, I did an operation. Oh, I did an operation. Oh, I did an operation. And so on. So yeah, this +1 has nothing to do with what you're actually doing, times 2, times 80, times whatever. So it's just the fact that you did something. So mul +1, that's what they did. Add +1, and then return the minimum of add and multiply. Yeah. So yeah, that's pretty much that. So if you wanted to find it a little quicker, you would, I guess, a little optimization if you're doing it like just for fun is just move this up, and then it'll do times 2 quicker and grow the number quicker if there's like a bigger gap. So if it's like 6 and then 84, you obviously want to do times 2, you know, more often than at the start. So yeah, let's go to the next question. Okay, recursive coding. This one should be a little easier, so I'll just go until 8 minutes. I'll just give you guys until 8 minutes. Okay, so it was 8 minutes. So let's start. So write a recursive function that returns the sum of all even elements in the integer array vals between indexes low and high inclusive. For example, 3 to 8. So let's see, 3 to 8 inclusive. So the evens in this range. So let's see, we have 19, 20, or sorry, that's not even, 24, 8, and 10. So yeah, we're gonna get 32 and then 10, so that's 42. So the whole idea is we're doing it recursively, and we're gonna want to include these, and we're gonna want to ignore all of the odd numbers. And when I say ignore, I don't mean you just want to stop. You just don't want to account for them. So let me get on the whiteboard real quick. So let me just drop a little examples. 3, 4, 5, 6, 7, and then 8. So 19, 24. Okay, cool. So there's two ways to go about this, because the whole idea is you want to scan across this whole like subsection of the array. So we're assuming that they're going to be valids, meaning they're going to be at least from here to here inclusive. So, or it can be any subrange like this or something like this, right? It could even be just one thing itself. So within that that given range. So they're going to give us something valid, so we don't have to check for anything like that. And we're just going to want to recurse in either direction. So there's multiple ways you can do this. Since you have a low and a high, you can either go right to left and then do the recursion right to left or left to right, sorry. Or you can go right to left, considering you have the low and the high. So really, if you think about it, if you're recursing and you add the numbers, it doesn't matter if what way you add them in, because addition is commutative. So like 24 plus 8 is the same thing as, well, this is a bad example, but 24 plus 8 from like 28 plus 24 is the same thing as 24 plus 8, like that, so it doesn't matter. If it was something else like division or subtraction, then that's a different story, but then, yeah. So we can go from this direction, from left to right. So I'll just do left to right. And we're going to start at 3. So let's see. What are we going to want to check at this point? We only care about the evens and adding the evens. So we can invalidate certain cases. So we're going to say, okay, 19 is not even. So I'm not going to hold any information on 19. You can effectively say this is 0. The sum for this is 0. When you see 24, you're going to say, okay, is this location at index 4 odd? If it's odd, then I want to count for it. Don't make it 0, make it 24. Same thing right here. So 8 is even. Here, you're going to say, okay, is 7 even? No. So let's just say it's 0. There's nothing there that we care about. Same thing here, 0. And then same thing here is going to be 10. So yeah, the whole idea is just to go from left to right, just like you would in a for loop. So for I equals 3, less than or equal to 8, and then you would just do your if checks like that. So it's just a 1D recursion left to right. So let's just jump into it, because it should be simple for you guys to understand. So let's think about it. When do we want to stop? There's multiple ways to do this right here, but what I'm going to end up doing, since I'm going low to high, so left to right, is after we pass the point that we care about, then I'm just going to stop. So I'm not going to stop at high itself. I'm going to stop at the next location after high. So I'm going to start right here with x's. So let's imagine we have this, and we have a bunch of boxes in between this here, so a bunch of like indexes. So I'm going to stop at the point right after it. So we can just do if low is greater than high. So that means that we've passed it, and we're just going to return 0, because now we're done. We've completely searched and looked through, like when I say search, I mean like you just passed over everything. So now we're going to want to account for whether or not something is even or not. So let's say, I guess you can say, we can call this whatever you want. I guess you can say cost or sum to this sum. So set it to 0, and then we can say if values at low mod 2 equals 0. So this is saying if it's even, then what I'm going to do is sum equals values of low. So in this current iteration at this given index, so let's say we're at 3, it would actually be 0. We would leave it at 0. We wouldn't go here because it's not, it wouldn't give you, mod 2 would give you 1, not 0. But when we're at 4, it would give you that. So it's going to set it to 0, or sorry, the 24 at that call. And then after this, at that point, we can just do return sum plus, and then sum even, vals low plus 1 high. So what it's going to end up doing is just adding whether or not it is. If it's not, it'll stay 0. If it is even, we're going to account for here, and then keep on recursing until we passed over the entire like subsection that we're looking at. Inclusive. So if it was exclusive, we would do this, or sorry, we would do this. But It's for inclusive. We can just, once we pass over, we're done. So once we hit 9, we just return 0 because we've gone from 3 to 8. So let me see what your guys' questions are. Array, yeah, exactly.
Wouldn't 9 be the highest index though? So like if low, like wouldn't low like hit 9 and you still want to add that number?
Oh, you're thinking like kind of like merge sort kind of thing, like merge sort and what's the other one? Quick sort. But no. In this one you want it. They give you 3 to 8. So they're saying between indexes low and high. So you don't want to go past it, you don't want to go you don't want to go before low, you don't want to go after high. So it's only within 3 to 8, like inclusive. So
Oh,
yeah,
okay.
so for example, if it was 1 to
If I did
6, it would be just 1 to 6.
So what I did for mine was I did if it's less than or equal to high, and then I did all that stuff else return.
If less than or equal to high. Yeah, that's fine because think about it. This is literally just saying, this is pretty much just saying if it's not, then don't do anything. But if you're saying if it's less than or equal to, then you're kind of like changing your code, kind of like you have all this stuff inside of this bracket. Yeah, it's fine. It's fine. As long as you have like you've accounted like your variable to be like let me just write it out. The solution's gonna come out like so. Yeah, so they did it kind of like how I ended up doing it. Let me flip it back because
Yeah,
that's
yeah, they did like that.
So let me just do it how you meant. So you were saying if you do okay, so this is pretty much saying if it's not, oh wait, let me see.
No. I
Sorry,
did,
0.
yeah, return
My
0
bad.
there. Yeah, that's
Yeah, I was thinking
exactly.
about
And
the
then had
wrong.
the rest of the code was pretty much the same there.
Yeah.
Except my variable name wasn't some, but the rest of the code was the same there. Exactly how you wrote it right now is how I did it.
Okay, I got you. Yeah, that's perfectly fine.
Okay.
That's perfectly fine. There's different ways to do it, but yeah. So that's that. Anyone else have a question? Okay. All right, cool. Okay, let's go into what is this? Oh my gosh.
Wait. I have a question.
Mm-hmm.
So,
Wait, give me a second. Have you guys heard from your teacher if permutation is going to be on the test? Because this is like a backtracking question, but
yeah,
they're not doing that stuff.
it might
Are
be.
they?
I don't know.
No, backtracking is not on it.
Okay, so that means permutation. Then permutation is backtrack. Okay, so let me skip this one then.
It might be. I have no idea.
It's a good question, but they're not doing that stuff. So
Yeah, who told us today in the lecture?
cool. All right. So what was your question?
Oh, like going back to the sum even,
Uh-huh.
like there's like the first if, which says if low is greater than high, return 0.
Mm-hmm.
Do you have to like why you didn't include a greater than or equal to?
Greater than or equal to, because I'm assuming that they give it to me like where it's at most, like I'm assuming at worst they're equal to each other. So that means there's at least one thing that I have to check. Like if they gave it to me where like low was 8 and then high was like 2, they're not going to give you that, if that makes
Okay.
sense. Like they're just
They're
giving
not
you something that's valid already.
Are they gonna give you something like 8 8?
Yeah, 8 also works on this because 8 is not greater than 8, so you're still good.
Oh,
But the
okay.
moment your low hits 9, that means like the way I like to think about it is like,
Wait, wouldn't
hmm?
I mean like they give you 8 8? Oh yeah. Okay, cool. I get it.
Yeah. The reason you stop at 9 is like 9, and then if high is 8, is because you like exhausted everything you were looking through. So now like you got nothing else to do. So yeah.
Cool.
All right, at 7:30, I'll go to the next one. I'll start this one. All right, so 7:30. So write a recursive function that returns 1 if an array of size n is in sorted order from smallest to largest with all values less than or equal to max and otherwise 0. No, if array stores 3, 6, 7, 7, 12, then is sorted A 12, 5 should return 1, but is sorted A 11, 5 should return 0. So let me make sure I get what they're saying. So this is the maximum value, but then this one is not the maximum value. Okay. So what they mean is you want to see if it's sorted and all values are less than or equal to the maximum. So in this case, where it's good is 12 is good because, they're all in sorted order and they are all greater than or equal to, less than or equal to 12. In this case, 12 is greater than 11, so it's not less than or equal to 11, like the whole thing, even though it may be sorted. So they just want you to check if it's sorted as well as if everything is smaller than the number that they passed in initially. So if they gave you 3, even though it's sorted, not everything is less than or equal to 3. So that's the whole idea. So pretty much what's going on is three, 6, 7, 7, 12. And let's do this one where it's 12, 5. So max is 12. And what does 5 mean? Oh, 5 is n. So n is 5. So that's cool. So we have to make it recursive, but we only have n, and n is 5. So that means the only way we can move through this array is with this information they give you here. And you guys might be like, okay, so 5, if you have 5 items, the highest index is 4. So if you just index directly into this, then you're going to run into issues. It's going to segfault. So one thing that you can do with this number to make it valid from the start is just do n minus 1. So that's going to be 5 minus 1, which is 4. So you can start looking at 4 and then go from there. So it's probably going to be a little hard to do the classic way that you start to check if things are sorted. So for example, if let me see. So if you can't check forward like this, or you can't check backwards necessarily, you might be able to add into your logic to check forward, but the whole idea is they give you a max variable. So I guess as you're going down the list, so 3, 2, 1, 0, you're updating this maximum. So it's okay, so first we check, is everything less than or equal to 12? So when I say everything, I mean let's start off. So we're going to see 12, and 12 is less than or equal to 12. So we're good to keep going. So now at this point, then we can move our maximum down to whatever this number was. So it started off as 12, but now what we can do is keep going and say, okay, now in this call, so we start off with 12 and then 5. We checked backwards by minus 1 and saw, okay, this is good right here. Then now we're going to recurse this way. Our maximum is just going to be whatever this value was, because think about it. If we're trying to check if they're sorted, then this number will be the biggest, and then eventually this number is supposed to be the biggest, and then eventually this one and this one too, you get to this point. So let's set it equal to 12. So now we're going to be at index 4, so right here. And we're going to check backwards, and we're going to see, okay, so is, let's say, array of n minus 1, is that less than or equal to our maximum? So our maximum is 12 right here, right? So we're going to say 7 is less than or equal to 12. So that's good. So now we can keep going. So we're going to keep going in this fashion. So then now when we end up going to this location, we're going to change our maximum, because again, the whole idea is you're checking if you're sorted. And if you're going right to left, then every number to your left of where you currently are should be less than or equal to the current number you are at, or the one you just passed. So that's why you just had this value in here, add this value in here. So now we got the 7 from here, not this one, we got it from here. So I'm going to see, okay, so we're going to have index 3. And let me just check the time. Okay, we got 2 minutes. Just close this up. Okay, so 3. And now from here, we're going to say, okay, so is 7 less than or equal to 7? So yeah, we're good. So this is going to be index 2 because we're going to do n minus 1. N is currently 3. So we're going to say a of 3 minus 1 is less than or equal to 7, which is good. So now we're going to keep going. And we're going to set the max to now be 7, even though it already was. And this is going to be 2. We're going to take a minus 1, a 2 minus 1, sorry. So that's going to be 6. Is 6 less than or equal to 7? Yes, we're good. So now we're going to keep moving forward. And we're going to keep checking and see, okay, now we're going to be at 1, and then we're going to take this value, put it in here. That's our new maximum. And we're going to see, okay, is a of 1 minus 1, is that less than or equal to 6? So is 3 less than or equal to 6? Yes. So if that is true, then we're good. Now let's think about it. We could keep going, or we could just stop here. So let's think about what happens if we keep going. So if we keep going, we can set our max to 3, but then our n will be 0. So if our n is 0, like when we're at 1, we know that we're going to do 1. So we're like kind of like right here, and then we're looking at this one because that's the only way we can traverse through the array. That's the only thing we have to move through. So once we get to 0, we know that we've exhausted it, because now when we do our minus 1, we're just going to be at negative, which is not valid. So you know that once you hit this index being 0, the only way you could have gotten there is if everything previous to it was good, if that makes sense. Because if there was any point where you had hit a base case, like, oh, it's not less than or equal to max, it's like greater. So let's say we had like 37. So 7 or 37 is not less than or equal to 7. So then we would have just stopped right here and then returned eventually that no, we're not sorted. So once you get to this point, or really, just this point, and you pass it, once you hit the 0, then now you know, okay, we're good. Everything is sorted. The only way we could have gotten there is if all of this was good. Comparing in pairs. So hope that makes sense. So let's just code that same idea up. So first of all, one base case, if n is equal to 0, then just return 1. Else if, now what we can do is, we know that we're not at 0, so we're not going to, if we do n minus 1, we're not going to be at -1, so it's going to be a valid index. So here we can check, else if, another invalidation case, if array of n minus 1, if it's greater than max, and that means we're going to return 0. That means we're not sorted. So that would be like a case where 37 is greater than 7, or see 93 is greater than our max of 6. So we would know we're not sorted then. And pretty much at this point, what we're going to do is just return is sorted array. And after we get through these 2 lines, we know that we're good because we've invalidated all the cases that we don't want, or that we might want, like this one right here. So therefore, we can just set our max to be equal to the current location we were just looking at, and then bring n minus 1, or bring it down so we can go on to the next pair and the next pair and the next pair. So yeah, this is pretty short code, but we checked all our bases. We're at the end, we're good. If we find a discrepancy that's not sorted in sorted order, then no. And yeah, if like otherwise, just keep moving down and reset the max. So let's see the answer. Yep, so exactly that. So n equals 0, 1, array n minus 1, max, yeah, and then is sorted, move it down, set new max, keep going. And I guess they have a different way to do it. Oh yeah, so pretty much they did like 2 elements at once. So they did like in this case, let me see what they ended up doing. They ended up doing something like, so you would have started off with n equals 5. So right here, after, so wait, let me see. So at this point, they would have checked like these two at once and then compared that way, and kept on going that way and so on. But let me see. Well, it's different because is it like you can write your own code or something? Okay, well, I don't even know why they included this because it's like not the same question, but all right, well, that's about it. I guess like if you're going by a different metric or something. But yeah, let's start on the next one. Oh wait, this was the last one. So let's end up going to the binary tree section. Okay, so I'm gonna start the timer at 7:30. We'll come back to it. Sorry. So let's start. Let me see what you guys are saying. Okay, so call the function on the left and right subtree and return height and compare those numbers and return that in. Okay, well, let's see. So the maximum off-center value, so they want to take the ABS difference between the height of the left subtree and the right subtree. So for example, an ABL has an off-center value of 0 or 1. Also note that we define the off-center value of a null node to be 0. It computes the maximum off-center value of any node in the tree. Okay, so let's see. So pretty much off-center, it could be something like so I'm going to do X's for null. Always do that. So this side would have a height of 0. This would have a height of 0 because they're null. And this no, sorry, height starts at -1. So the height of this one would be 0. Because what you do, you take the maximum of the two and add 1. Then I'm just going to keep going and make the tree so we can see what happens. Because it just calculates the height for you. And by the way, it's not saying if it's like a balanced tree. So I'm going to just, go a bit based off. Okay, so it would be something like this. I believe I might have messed these two numbers up, but let me fix it. I guess this side would just be 0, 1, and 2. I'm kind of rusty on ABL, so if it's wrong, like, yeah, you just get the idea. So maximum off-center value. So we want to get the maximum difference between these two at any given point in the tree. So in this one, we would have a maximum of 2 being the difference. So let me just close this up before it starts. So I guess at any given point, since we have the height attribute, so we have the height like this at every given node, what you can do is, yeah, you're going to end up recursing throughout the entire tree, and pretty much try to find the best answer. So let's say, for example, you end up recursing down this way. So you're going to find the best answer at this point. So right here, you can say the best off center would be some -1, or they said it would be 0 in this problem. So 0, 0. So it would just be the difference is 0. Right here, you can say it's 1, and then this is 0. So difference here would be 1. So at any given point, we're just calculating, we're looking down to our left. But the thing is, we're not necessarily just taking the answers that we get from our left and right. At every given node, even though we're going to end up recursing down these ways, like when we come back up, when we come back to this point, so we're going to recurse this way, right? Then like I'm doing like post order. So post order on this subtree would be something like start right here, go down this way, then you actually end up coming back up, but then you recurse back down. And then now is when you would like print this node is kind of like how it would work. So really the whole flow would be you recurse down this way, go to this one, and then you come back up to this one. So you would recurse, but then the thing is, when you come back up here, ultimately after looking at this subtrees of it, the left and right subtrees, then you would just index into, or not index, but like arrow into root left and then check the height. So you would get the height of this. So let's say this is like 3, and then the height of this one would be 1. Then at that point, then you can look at your left and your right. And there's going to be some cases like if it's null, if it's not null, and so on, that you're going to have to handle. But after you come back up from processing, then you're going to look at the left and the right, the current one, and then you're going to compare what you have at the current level between the left and right subtrees to what you ended up returning from the recursion. So I hope that makes sense. It's kind of confusing because like we're going down recursively, getting the best answers from the entire subtrees under us. But then once we end up coming back, we're looking one level right under us. So maybe I should probably draw a better tree to explain what I'm trying to say. But let me draw a deep tree on one side. This one's kind of like a confusing one. So null is 0, they say. Okay, so the answer here is obvious, but the whole idea is you're going to recurse down. So you're going to start here, go all the way towards the left. So we're doing post order. So we go all the way left. We take the answer from this right here. So that's going to be 0. Then we're going to go down to the right, take the answer from this entire subtree. So this one's going to be 0 and then 0. And then now we're going to compare, okay, what's the height right here based on, like the answer is going to be what is the height of the direct subtree. So it's just be 0 and 0. So in this one, you're just going to return ultimately an answer of 0 back up to the call that called it in this one right here. But then when you're at this level, even though you ended up recursing downwards to this node at this level that I'm right here, you're going to say, okay, so to my left, I have a null, so I have 0. And then I just ended up getting an answer of 1 from this node right here when it returned, or sorry, of 0. So let's compare 0 and 1. Is that bigger than the 0 that I just ended up getting from this node after it recursed backwards? So I hope that kind of makes sense because you're going down the paths. So you're going down all these ways, but then you're comparing what did I just get from under me on the left and the right? And let me compare that with where I'm currently at. So directly what's under me. So getting the best answer from this point on, and then comparing answer 1 and then answer 2 with the answer you get from here, which is just going to be whatever the heights of these two are. So this would be your like kind of like your answer 3. And at that point, you're taking the maximum of these 3. So answer 1, answer 2, and then answer 3. I hope that makes sense. If you guys have any questions, let me know, because I know that was probably pretty confusing. So as for getting into coding it, so if we have a null case, we know that it's going to be 0. That's what they said in the problem. Then now we're going to want to store the answer, the best answer that we got to the left. So int best left. So the best off-center value in our left subtree. So that would look like next off-center value, move to the left. Then we're going to do the same thing for the right. So best right equals max off-center value, move to the right. And now at this point, we're going to compare exactly where we're at. So we're going to want to know if we even have a left, if we even have a right. So we can just do it like this. So we can say left subtree height. So this would be, and I'm going to do like a ternary statement. So I hope you guys are familiar with that. So if root left does not equal null, then what I want the value of left subtree height to be would be root left height. Else, if root left is null, meaning it's false, then this condition is false, then I'm gonna return 0. And then I'm gonna do the same thing for the right side. So if I'm at a current node, I've already recursed left, right, and then I come back up post order. And now I'm gonna see the right side and get the heights from the children directly under me if they're there. And now the entire idea is to take the maximum absolute value between all 3 of these. So we can, let's just end up doing like this. So return maximum. Stick the maximum of the left and the right first. So max side height. And we're going to do max of best left and best right. And now for these, we're going to want to do absolute value. And the reason is that since we recurse, whatever answers that we get from this, since we ended up calculating them in this fashion, if we just do ABS on these, eventually it's going to be correct for when we recurse back upwards, like what we get directly from these 2 answers. So pretty much by fixing these 2 to be ABS, the answers as we come back up from the recursion will also be like absolute value, like positive, or just 0. So now we can set the absolute value difference of current to the left. ABS. Did he tell us what the oh no, he didn't give us an ABS function. So I guess to calculate ABS, let's just do this. So if right subtree height is greater than or equal to left subtree height, and we'll just say ABS if current equals right subtree height minus left subtree height. And in the other case, that means that left subtree height is greater than right subtree height. Then we're just going to do the opposite. So we kind of have to calculate ABS ourselves. And now at this point, we already have the max side height. And then now, since we have the maximum between these 2, we're going to have to take the maximum between the ones from the left and the right that we got and the ones that we're currently in. So return max of max side height, and then ABS different of the current level we're at, like our direct 2 children. And this should give us the right answer. So yeah, this is like one of the harder ones. So yeah, if you guys like kind of lost on it, don't feel bad, because this is probably not what you're going to get. Generally, the tree questions tend to be way easier than something like this. This one and then another one are like, people think are the hardest ones.
Could you explain the what you did for like left subtree height, right subtree height, like the syntax?
This? Oh yeah, sure. So pretty much what I'm saying here is if root left does not equal null, so it's saying that if I have a left, right? So if I have a left node, this, so after this question mark, the first thing right here, so this right here, this is what the value of left subtree height is going to be if this condition is true. So you can think of it like an if statement. So this is your if this is true, set this value equal to this. Else, if this is false, set this value equal to 0. Did that make sense?
Yeah, that made sense.
So you can just think of it kind of like, I'll just write it a little differently. So we can just start this off at set equal to 0. It's kind of like that other question that we did, but that's just some easier syntax, make it quicker. So if root left does not equal null, then we just said left subtree height equal to root left height. So that might be an easier way. So I'll just write it like that for everyone. There we go. So that's kind of what I meant. Okay, so now let's go to this one right here and let's see. So see what they ended up doing. So their answer is a little different from how ours look, but so if root equals null, return 0. So we have that here. That's good. If root left equals null and root right equals null, return 0. So you might not see this in this code, but it's actually happening. So just think about it. If this is the case, this means that we're at a leaf node. A leaf node is when you have no left and no right. So you just have two nodes, a left and a right. And then best left, since it would be null, we would end up getting a 0 from it. Best right, since it would be null on a leaf, you would be getting 0 from it. Then we take the maximum of 0 and 0, which is just 0. And then we're gonna calculate the left subtree height by just looking down at our left child. But the thing is, we don't have one. It equals null, so this would not be set to anything. It would just stay 0. Same thing here if it's a leaf node. If this is equal, if we have a leaf node, there's no right, so it equals null. It does not equal null, if that makes sense. So there's nothing there, so it is null, meaning this will stay 0. So now we have 0, 0, max of 0 is 0, of 0 and 0 is 0. Then this is going to stay 0, this stays 0. And then you calculate the absolute value. So if 0 is greater than or equal to 0, it's equal. So you're just going to do 0 minus 0. So ABS difference current is 0. And then max side height, it was just a max of 0 and 0. And then ABS diff current is also 0. So it just returns 0. Yeah, I know I said 0 like a million times, but that's it. It works the same way. It's just you don't see it directly handled, but it's the same thing.
If you did it with an actual like if you used actual like heights of left and right, how would it work through? Like, because I'm a little confused on why we're finding the max side height and what we're using that to do when we do max. Like I maybe I'm confused on what the question is in general, but
yeah, I'm not gonna lie, most people are pretty confused on that. But the whole idea is like this is just one of those questions that like the moment I saw it, I knew. I was like, dang, this one is rough. This one is rough. So the whole idea of what you're calculating is that there could be an answer somewhere deep in the tree. So I'm not going to draw another one, but let's say somewhere very deep. So I'm going to draw a triangle that's going to represent like a subtree, right? So this can be like a million nodes, or it can just be like 3 nodes. But let's say there's something down here. There could be a case, and let's also draw another one down this way, and then just this, and then that's that. So let's say you get an answer down here that might be 4. So somewhere in here, there's an imbalance of 4, right? But then let's say right here, somehow there's an imbalance of 6, because you're going to have like, let's say you have 6 and then this is 0. So this is a leaf, but then the left side is actually 6. and this is 0. So the best you had gotten from this whole subtree, it ended up returning 0 up to this node. This one, let's say this was let's say this one was also 4. So this one was also size 4. Then you would have 4 and 4. So you would take the maximum 4. And let's just make it simple. Let's say there's going to be 4, the best answer. So after this point, oh wait, let me change this a little. Let's say this is 10. So if you got a 4 from here, and then you see there's a 10 somewhere in here, you're going to also want to check the current one that you're at. So you're going to check immediately to your left. So let's say something's right here and right here. The answer of these two, the difference of height between these two nodes right here, might be better in terms of maximum than the 4 and the 10, if that makes sense. Like, let's say for whatever reason this was 56. Then in that case, taking the left, so this node, let's say this was 26 and then this one was 30. But the best answer under these two was 10, and then in this one it was 4. You're going to want to see what's the best throughout the whole tree, which is why you're going to want to recurse, get the best answer as you come up, and then check where you currently are. So where you currently are, let's call this node A. Let's call this node B and this node C. B and C, the difference in height between them might be better. Oh, shoot. For it to be 56, it would have to be like 86, for example. So 86 minus 30, the absolute value between those two would be 56. So that would be better than either just taking a 4 or a 10. So then now, at this point, you would end up returning 56. And let's say the difference in height between these two was just like 3, right? So you would get the maximum of 56, 3, and then 0, which is just going to be 56. And then from this side, you can have, let's say, 80, right? So 80. So let's say you get an 80 from overall this whole tree. So you're going to return 80 up here. But then let's say the difference between these two nodes is like just 5. Then in that case, you're going to take maximum of 80, 56, and 5. Because at every given point, you're checking the height difference between your left node and your right node. So if we're right here, we're going to check directly our left and right and then compare that way. I hope that makes sense. It's pretty confusing.
So you're checking the height of your left subtree, you're checking the height of your right subtree, and then you're checking the difference of those subtrees, and whichever value out of those three is the highest
exactly
is going to be returned to your root.
Exactly.
Where are you saving that? So for example, in that situation, 80, 56, and 5, we know we're going to return 80, right?
Yeah.
So where would 80 be stored in the, like, because I was confused where you're storing that value of 80.
So we can say like 80 is when you come back from the recursion, right? So 80 is like when you come back from the recursion, but then right here, you can say that what I have here, where I'm checking the left and the right, they just did it a little differently, so you don't have to like do these checks, but you would store 80, for example, from the recursion, then you would have stored 56 from the recursion towards the left, but then the 5 would be the difference between like these two numbers, left subtree height and right subtree height, which yeah, and then you take the maximum. So this value represents the maximum between best left and best right.
80.
Exactly. And then this is just 5. So then
just
you would
a
just
different
yeah.
Return. Oh, okay. It started to make sense now.
I'm not gonna lie.
Is this like a representation of a trie, or no? This has nothing to do with that.
No. This is binary tree only. Binary tree just has at most 2 children. But yeah, it was one of the harder binary tree problems. Maybe the next one will be easier. Okay, yeah, it is cool. So I'll let you guys try that one out for 7:30, and then we'll go from there. Oh, by the way, Juan asked a question. How come they use ABS in the function in the answer? So there's some questions, it's weird, but there's some questions that they say you can use something, but they don't directly tell you. So you can actually, they give you like a formula sheet on the day of the exam, and also you can find it online where it tells you all the functions you can use. So I honestly, since I took mine in January, I forgot about that. So like, yeah. So but all the math.h, string.h, even though they don't include it directly, and actually now that I think about it, they did include it. Let me see. Yeah, they had like include math h at the top. I didn't see it, but even if they didn't have that, if they said use absolute value to whatever, you can just reference it because they assume, like you can assume you have all those functions if you need to do it. So yeah, I just forgot about that honestly. But this is the same exact thing. Oh, by the way, I know sessions are 7:30 to 9:30, but last time, since there's certain things that get a little hard, I extend them like probably like an hour after. So like probably gonna be here until 10:30. If you guys have to go, it's whatever. It'll be uploaded. But yeah, I tend to push it back a little longer. Yeah, the first one was uploaded. All right, I'll give you guys another 15 seconds and then it was uploaded. I actually sent the link earlier on, but I don't think you joined them. But here you go. That one was DMA, linked list, stacks, and queues. All right, so let's get started. So the following are 3 tree traversals produced by the same exact binary search tree. So binary search tree, it's important. That's why I underlined it. So using your powers of inference to determine which one is which. Fill in the blank in order, pre-order, post-order. All sets of answers which don't contain each traversal exactly once will be rewarded 0 points automatically. Cool. All right, so let's talk about the different traversals. So when it comes to binary search tree, the coolest one to know is in order, because since it's a binary search tree, let's just think about it. Let's just dissect that term, binary search tree. So we can think about binary tree, right? And we can also think about binary search. So if we think about binary search, we know what's the prerequisite for binary search. In very basic cases, it's that what you're searching on has to be a sorted range or has to be a sorted array or group of numbers or sequencer and so on. So we know that binary search, to be able to say, okay, if this number is smaller, go to the left. If it's greater, go to the right. We have to be able to look through things in a sorted set of numbers or collection of numbers. So in order requires, or it prints the numbers in a fashion that they are in order, in sorted order. So the only one in sorted order is the last one. So that's in order. So let me just do like A1, A2, and then A3. So this one is in order because it's in sorted order. Now, there's a couple different tricks to do this really quickly, actually. But now we know that one of them is in order. We know which one it is. It's pretty easy to tell. So now we only have two other options, pre-order and post-order. So when it comes to pre-order, we're going to want to see I guess you can use the property of in order to kind of reconstruct it. But one trick for pre-order is to see which number is first in pre-order and which number is last in the post order. So if you see, for example, in this case, we have 18, right? So 18 is at the start of the first line, right? So in the second line, we have so we have 18 at the end. So at the start of the first, we have 18, and then at the end of the second one, we have 18. So pre-order, it will always print the number first and then recurse. So the first number it ends up printing, meaning the root of the tree is 18, okay? So in post order, it ends up recursing left all the way, right all the way, and then you come back up to the root. So recurse, then print. Pre-order is print, recurse. So when I say recurse, that means left and then right. And then you would start over at that node again. So since they're in a way kind of opposite, like when they print the root, you can easily tell which one's which. So we know that for these two numbers, pre-order is the first, or these two sequences, pre-order is the first one and post-order is the second one. That's always a property. That's why you can tell really quick. Sorted one, easy. Whichever one has the initial of 1 at the end, that's post. And the only one left is pre. So that's how you can tell. Now let's see for B. So B is, what is the value? What value must be at the root to produce the list? So we just answer that question by knowing that simple like fact. So that's going to be the 18. C. So using big O notation, what is the best case runtime for searching for a particular value with n nodes? So this was kind of weird sometimes, honestly. Typically, it's log of n. I remember, I don't know if it was exactly on BST, but there was something on BST that was O of 1. But generally, we're going to have log of n. So I'm just going to write log of n. The only case it would be O of 1 is if it's literally the root. But I guess they try to think of it in, pretty much they try to think of it in general cases, not like on average. So not like the really small edge cases, you know. So, and then let's see, D, using big O notation, what is the worst case runtime for searching for a particular value in a binary tree, a regular old binary tree, not necessarily BST. So back to the whole term of BST and binary search tree and all that stuff. We dissected binary search tree, but there's no binary search in just binary tree. So that means we don't have a data in a specific order. So we cannot say everything to the left will be smaller and everything to the right will be bigger. So there's no organization, and therefore we can't efficiently do anything and cut down. Because the whole idea of binary search and like binary search tree is that at this point, if I decide, let's say I have a tree of this size, right? So it's kind of like why the runtime works. And let me see how long I have left. I have a minute. That's good. So this is a small example, but if I'm at this point and I'm like, okay, my value is actually to the left, we're going to go this way, right? But what ends up happening is you end up cutting about half of the tree by doing that. So that's kind of like the thing that justifies like the logarithmic runtime. Then at this point, let's say it's greater than whatever this is. So you're going to go towards the right. So that's going to cut off about half of what was left. And then that's why you can say log of n, like average. But in the case of a regular binary search tree, there's no organization. You don't have everything to the left is this, everything to the right is that. So it would just be O of n. You would have to go through the whole thing because you know, there's no organization. Then E, using big O notation, what is the worst case runtime for searching for BST with n nodes? So let me just show you guys. This was a pretty simple example. So in this one, this was a perfect binary perfect binary tree. So everything is like completely full. It's, you know, every node is there and so on. So it's nice and easy to see the example, and you're cutting about half every time. But when it comes to a bad BST, you can call it. Since it's a BST and not an AVL, it doesn't necessarily have to be balanced. So the worst case is if the tree is not balanced, meaning you're not cutting about half each time. Because remember, the height of this tree right here would be the same if the tree was just, if you just erase this right here, it's still the same exact height. But you wouldn't, let's say you wanted to go, like, if you end up going to the left, you're not necessarily cutting exactly half, but it's about half. It's kind of the whole idea. It's like an approximation. But the case where you wouldn't do that is, let's say you have a binary tree that's completely one-sided or very like, it's heavily on one side. So one of the weights is way bigger than one of like this. So this, let's just say this is null. Then you have something like this. And then after this point, then you can have maybe something like this. But generally, everything is kind of in a straight line. So on average, it's about n nodes you'd have to traverse to be able to check if something is in there, like to insert. So let's see, this was like 50. If you wanted to insert 100, then sure, you would insert right here. But if it's one-sided, let's say you wanted to insert like, let's say this was 10 down here. If you wanted to insert 9, you would have to go through about however many nodes, like n nodes, to get to this point, then add 9. If you wanted to add 9.5, go again through this many nodes and then go down, and so on. So that's kind of like the whole idea. So the worst case runtime would be O of n. It would pretty much look like a linked list, which if you guys look at it, yeah, it looks like a linked list, just drawn a little differently. Let's see what the answers were. Yeah, I knew there was some weird case. So pre-order, post-order, in order, that's good. 18 is the root. And yeah, this is what I meant. Like, for some reason, they say the best case is just the first, which it would just be like the top element. But generally, they try to think of it in average case. But just remember, when they say best case runtime for BST, just assume it's O of 1 for searching and inserting. For the most part, it won't be, but I guess they were looking for literally the best one. So yeah, this was one of the weird ones that I had mentioned. Then O of n, that's good. Oh, I didn't even, did I skip one? Oh wait, no, I just forgot to say. Yeah, so this one was also O of n. The last one we did, the linked list kind of looking one. So yeah, that's that. So this one, they just assume, I guess it's at the very top, and that's about it. So let's go on to the next question.
Wait, can I ask a quick question?
Yeah.
Could you go over the difference between the pre-order and the post-order, how you found that one more time?
Like how I found it right here?
Yeah.
Okay, give me 1 second. Let me.
The in order one is just like when they're like pretty much literally in order, but like I'm kind of confused on.
I got you. All right, let me see if I can reconstruct it a little. Okay, so this is what the tree looks like. Let me just make sure. So 9, so 19. Yeah. Okay. Yeah. So this is what the tree looks like. So let's calculate the pre-order real quick. So by the way, just to reconstruct it, I just kind of like use what I knew. So this might be actually a problem that you guys might get. So let me just talk about that real quick. So the way that I was able to do it so quickly was I know what the root is. And then I can look at in order to see everything that is to the left of it. So this is everything to the left. So if it's less than 18, which is the root, it must go to the left of it. And then from there, I just follow pre-order. Since pre-order goes to the left first, that means for this to be the next item after 18, it must be the first one to the left, and so on. And then I just use like BS3 properties. What's lesser than is to the left, and and greater than to the right. So that's why I was able to reconstruct it real quick. But okay, to get them, the way I like to think about, let me use a better color. So the way I like to think about the pre-order is you're going to start at this node, okay? And then you're going to end up going as far left as you can, but the whole thing is you're printing as you go. So 18, 14, 12, and then 9. And then in this example, you're going to pretty much go to the next available left that you have. So notice how this is null, this is null. So now you would really be ending up going to this one. That's 31. And now from here, we're going to go all the way to the left. So we're going to have printed 24, 19. And there's nothing to the left. So now we're going to just go down towards the right. So we're going to have 22, 23. And then from this point, we're going to find the next, like the next right that we can go to. So it's not going to happen until we end up going back up to 36. So it's very just for 36. So let's see. Let's follow this arrow. So 18, good. 14, 12, 9, then 31, 24, 19, 22, 23, 20, or 36. So yeah, that's kind of pre-order. So pre-order, the best way you can think about it is you're like hugging the edge of the tree as you go. So you just want to like fit it as closely as you can. So if I were to draw it out really quickly so you can see like the entire like flow of it would be that makes sense. So let me just draw another example of this one. So let me just copy. Okay, that's the wrong thing. Let me just copy this over. Okay, so again, the pre-order. And as for post order, this one's a little different. So this one, it's going to look like I'm going all the way down towards the left. So you'd think there would be an arrow or like a path like this, but really, I think a post order, I actually start from the leaves. I don't start from the top and go down, 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 and whatever. I start from the leaf because if you think about it, you recurse as far as you can. And what's the base case always? The base case is always when you're null. So you're always going to start at any leaf. And if you notice, any tree always ends in a leaf, like ultimately. So if this 9 was not here, it would be at like you would have printed 12, and then you would have gone back up because there's no left, there's no right if this 9 was not here. So in this example, if you were going to do post order, you would not print 18, not print 14, not print 12 yet. Not print 9 yet. See, oh, I'm done with left, I'm done with right, and then you print this. And then you would come back up here, go to left, oh, there's nothing there, okay, we're done, now print this. So that's why I start at the leaf, because the trees always end at a leaf at some point, and specifically post order, it doesn't do anything until you get to a leaf. So I actually started like this. So, right, so I'm gonna do this and draw like a little arrow so you can see like the direction. And then from here, now at this point, I would end up going back up to this node in the recursion, but on this side, there's nothing left to go to. So I'm just literally going to jump to the next leaf and then go from there. Then at this point, I'm going to keep going, jump to the next leaf, and then I'm going to end up back at the root. So I hope that kind of makes sense why I start at the leaf and then I jump from leaf to leaf. So I'm pretty much jumping from the nearest leaf to where I'm at any given point. So This is the nearest leaf, like so you always start towards the left, go up, then before you have to go back to the node that has like something to its left, you just go directly to the subtree of the left, but then you go all the way to the end. So that's why I jumped down here to the leaf. And then from here, I go like that, and then that's that. So pre-order 18, 14, 12, 9, then 31, 24, 19, 22, 23, 36. Then post order 9, 12, 14, 23, 22, 19, 24, 36, 31, 18. So yeah, if you just follow like that, jumping from leaf to leaf after you're done with everything along the way that you use to get there, then you're good. That's kind of like how you can think about it.
So in post order, typically the root node is always the last node printed. It should
Always.
Because
Not
you're going,
typically,
so you're
always.
starting from leaf nodes, printing all the way until you get to the root, but not the root, then go down the right tree, then go down left until you get to a leaf node and then print back up like that.
Exactly. Let me do another example, because this example is
Oh,
kind of easy. Or it's like it's not as complicated, but I'll just do one more so you guys can see what I mean, because it makes it a lot easier. And that's like stuff that I realized over time, but yeah. Okay, so the values don't really matter since we're doing post order, so I'm just not going to write values, but this is post. So again, I'm going to start at the leaf. So right here. And now there's not like I don't want to go to the parent of it until the very end. So the parent in any given subtree, the parent is going to be the last thing I process. So that's like my whole thing when I did this jump right here, like why I kind of ignored 18. So yeah, the parent is the last thing you process in the subtree. So this is a better example. So I'm going to ignore this one, and then I'm just going to go down to the next leaf. And then go up. Oh, shoot. Go up. And then now you have to stop holding it. There we go. And now you're going to go to the parent after you're done with everything else. Now from this point, I'm going to ignore my parent. So I'm going to ignore that guy. And now I'm going to go to the next leaf. Right here. And then let me just try it better. Right here. And now I'm going to keep going up because there's nothing else to process in the subtree. Nothing else is processed. Nothing else to process. And now I'm going to ignore this parent because there's something else on my other side. So now go this way. Now I'm done with everything under this parent. So now we're going to go to it. Now we're done with everything on the side of this parent. So now we're going to go to it. And I'm going to ignore my parent. Now I'm going to go to the next leaf node. Ignore the parent, go to next leaf node, go to parent because there's nothing else on this side. And then now you're just going to go all the way back up, straight up. That's it. Because you process everything in under this guy. And now by processing everything under this guy, you process this one. Then you just process this one. And now you process this. So now, then you're good. Now you can end up at this one at the end. So that's how it works for post order. So I hope that made sense. All right, let's go on to the next one. That one took a while. Okay, so I'll leave you guys until 7:30. All right, 7:30. So let's see. So write a recursive function to find the leaf node in a binary search tree, storing the minimum value. So thus, of all the leaf nodes in the binary search tree, the function must return a pointer to one that stores the smallest value. If a pointer is passed to the function is null, empty tree, the function should return null. So it's always important, even though they tell you, so you can like infer, but It's always important. What I usually do, first thing I look at after reading, yeah, look at the struct. But then I look at the return type because this will tell you what you're dealing with, you know. So you don't mix it up. So you don't think it's like a value or whatever. So let's get to drawing. So let's say you have a binary tree, or sorry, a binary search tree. So if it's a binary search tree, let me just add some values. Okay, so let's say you have this binary search tree, right? And you want to find the minimum leaf. So you would think, oh, it's so simple. Why don't you just go down to the left? Because since we know in order, like the whole binary search property, towards the left is going to be everything that's smaller. So just end up going to the left. But that would fail if one case you have something like this. Then you would have to say, okay, there's nothing to the left, so go to the right. So this would be the minimum leaf. But let's think about a different case. So in this case, let's say we remove this right here. Then now it's still the same case. Oh, just go all the way down to the left and get the first leaf. So in this case, we're fine. But let's say we don't have that, right? So far we've only gone to the left. We've only been looking left and then we went to the right once. But now in this case, let's make it a little harder. Let's remove all this. Let's say it looked like a linked list, right? So we would start off here and we have nothing here. So this would just end up returning null because that's the base case. It should return null. So return null. So for null, I'm just gonna write n because it's kind of hard to write with this. So I'm gonna end up recursing. So we started here, went to the left, we got null from the left. So now let's go towards the right. And we're gonna go to the left because we're trying to find like the smallest leaf. So in theory, it should be on the left. So we get nothing, right? So null. I'm gonna return n. Now we're gonna go towards the right because we still haven't found it. Now, see null. Again, we have our n. Go towards the right. You get the whole idea. Now we're gonna, oh damn, I drew this on the right, but I drew it towards the left. Okay, let me fix that. There we go. Oh, I actually meant to make it to the left. I just drew it weird. Never mind. Yeah, it's lesser than, so yeah, that's what I meant. My bad. Okay, so we didn't get null from that. We wouldn't have gotten. So from here, we would see, oh, we have a left, so let's go down that way. And then from here, this is a right child. So we're gonna check left first. See, oh, it's null because there's nothing there. So we're gonna get n again. So we still haven't found our leaf, but then once we get here, we can check if it's a leaf by saying, is the left and right null? In that case, it'll be a leaf. So now in this case, we found our leaf. Therefore, we can just return that node. So whatever, let's say this is node, it has a pointer address of like 100. So we're going to return the address, like the pointer to it. And we're going to say, okay, so which one, do we have something that's non-null? If we have something that's non-null, return that thing. So for this whole call that goes down this whole path, we're going to return ampersand 100. Because that's like the node containing 237. So Then we're going to return the same node because we had like nothing towards the right, and we passed it up. Now, yeah, we ended up returning this from there. Now we're going to see null and an actual node. We're going to see, let me pass it up. We're going to see null and then actual node again. Now we're going to pass up the actual node. And then at this point, we're going to see again a null and then an actual node. So we're going to, so again, I said ampersand 100 because that's like the node containing 237. So you can say you just ended up returning the node containing this value. So this is what I mean by this whole thing right here. So that's like the address to it. The addresses, yeah, I know, but I just said it as an example, like just ampersand 100, just so you guys can get the idea. So the node containing 237 in memory is going to be, what you end up returning. So you're going to prioritize. It's kind of like, okay, where'd it go? Okay, well, you're going to end up prioritizing whenever you have a node coming up versus when you don't have one. So let's just get to coding. So the base case, if there's no node, so if root equals null, it's going to return null, because that's what they say to do. And another case is if we have a leaf node, which is what we're looking for, and we can say if root left equals null and root right equals null, that's a leaf node. Therefore, just return, this would be like your ampersand 100. You would just return the node itself. So it's just address in memory, so roots. Right? And then now we're going to want to compare the minimum, right? So it's kind of easier to see if we have something coming up towards from the left, or if we have something coming up from the right, then we're just going to want to return the first thing that comes up that's non-null. So an easy way to think about doing that is using an OR statement. So if you guys are familiar with OR, it's like if you have, for example, you have true or false, it'll try to find the first true. So when this has the first true, it won't keep executing this part of it because you already found the first true. Meanwhile, if we had something like false, and then we had true, we would see, oh, this condition isn't true, it's false. So then let's go on to the next and to the next until you hit true. But you hit true and then it's done. So what we're going to end up doing with that, the whole point of me mentioning that is we're going to want to get whatever we get from the left. So this would be a BST node left. Because the whole idea is everything to the left will be smaller than everything towards the right. So if we do find mid-leaf root left, we're assuming that we're going to get something from the left. And if we get something from the left, meaning left does not equal null, we have a node coming up on that side, we're just going to return left. I hope that makes sense. And the whole idea of doing it this way is to just cut off at that point. So we don't have to search the right if we found it on the left. Otherwise, what we can do is we can do return. Actually, let me just write it down simply. So return, or not return, BST node, star right. We're going to get find and leaf and on the right. And now what we're going to do is return right. So the whole thing is if we didn't find it on the left, then it can only come from the right. And if there's nothing on the right, that's not going to happen because the whole idea is if the root is null, it's just going to return null. And if you have no left and if you have no right, then this base case would have handled it. So in this case, if you don't return here a left, then that can only mean that you have a right. Because if not, then these other cases would have been handling it. So this is one thing you can do. And what I mentioned about doing like OR, the OR operator would be something like this. So you can end up just doing, so I'm going to refactor this a little. because we're using the property of like the logical OR, which is like these two lines right here. So we can erase all this actually. And like I said, if whatever is true, if this is true, then we won't have to process anything past this point. It doesn't matter how many dashes or how many like possible options we have. The first true, it stops. So if we find it on the left, then we're just going to return that. Else, if we don't find it on the left, then it can only be on the right. And the reason why like you're going to know if there's nothing on the left, it would have to be on the right is again, the leaves always end at a, or sorry, the tree always ends at a leaf node. At the extremity, at the very bottom of it, there's always a leaf node somewhere. If not, like there's something wrong, you know? So that's the whole idea. If you don't find it on the left, you'll find it from subtree on the right, and you'll return the minimum leaf at that point by short circuiting it. So if this is true, then stop and return this answer. So that implicitly like handles that. So same thing. If root left equals no and root equals no, return root. So we have the base case for the leaf. And if root equals no, return no. We have that as well. Then this that they did right here, root left does not equal null, then they return whatever they got from the left. So this is essentially the same exact thing. They just rewrote it a little differently. So if left does not equal null, that means that we had to have something to the left, because if not, if we went left and then root became null at root left, then we would have returned null. So by checking left does not equal null, we know that like it's not going to end up being null. And then this would be just as fine to return as with this. It's the same exact thing. And otherwise, then you're just going to return right, which is the same thing we did here. This also works as well. So again, if it does not equal null, cut off here, else search, and then you'll find it here. So it's the same idea.
They wrote find min left instead of find min leaf.
Wait, what happened?
In the answer, they wrote find min left instead of find min leaf. Like in terms
Yeah,
of their function.
yeah. They mess up stuff. Like, I don't know. It was like, it's funny because this session, there was a couple of questions that like, they just assume, or they just make it seem like something is the case, but then like, it's like the flood flow question. The one where it was like, if it was flooding or not, they don't even check if it's flooded. So you end up like going to stuff you don't have to. So there's errors here and there in the answers that they have, just like that. So that's another example of that. But yeah, it's one of those things. All right, let's go on to the next one. Oh, this one was from the one that was just under the last foundation. I remember seeing it. All right, and by the way, this is the last binary tree. Then we're going to go on to tries. All right, it's 7:30. So let's see. Demonstrate your understanding of recursion by rewriting the following recursive function, which operates on a binary tree as an iterative function. Okay, so we're rewriting recursive into iterative. Then in doing so, you must abide by the following restrictions. Do not write any helper function in your solution. Do not make any recursive call. Okay, so since it's iterative, they don't want any recursion. So this is something, when I first saw this, I thought it looked kind of weird, because it's just something that it is a weird kind of question, because it's like, it takes away from everything else that you've seen. Like converting from recursive to iterative, there's never been a question like that. It's more like, oh, you do not write in recursive, just do this thing iteratively. So this one you're converting, but one thing to notice about this question specifically and the way the code is written, if you notice for every of the conditions, it's either a base case, so 1 or 2, or on the returns, you're only making a recursive call to one direction. So that's like really key, because if you were doing 2 directions, then you have to like, it could be done iteratively, but then you'd have to traverse a tree like and have to be able to keep track of what's coming from the left, what's coming from the right. And the way you do that is with like a stack, but that's way out of the scope of this course. So in terms of CS1 thinking, you only have to go to the left or to the right at any given point. So if you think about it, it's kind of like when you're in a binary search tree, you're like going to the left or to the right. They don't say if it is one, so just don't assume that. But the whole idea of making one step at every given point is there. So you can simply do it through a for loop. And of course, you can handle it at these different base cases. So whenever if root is null, return 1. If root left equals null and root right equals null, return 2. So that would be a leaf case. So I just want you guys to notice that, because that's pretty important to making this question a lot simpler than it looks. We're only going to be making one movement at any given point. So let's start off. So I'm going to start off with a node called current. And beforehand, let's just check root equals null. And we can just return 1. That's a quick base case right there. And let's see. So another observation is anytime that so when you're null, meaning the first thing they give you, so this root is null, just return 1. If you're at a leaf node, you're going to return 2. And you're always doing a multiplication. So another thing also is if you don't have a left, you're going to go towards the right. And if you don't have a right, you're going to go towards the left. So you're kind of going in opposite directions at every given point. Yeah, you also have this base case as well. So let me just draw a quick example so you guys can kind of see how it's working. So it's going to be something like, okay, so let's see. Root does not equal null, so we're good. So now it says what we're going to do is check our conditions. So right now, we don't have a left, or we have a left, we have a right. So none of these conditions are going to be hit. Let's see what else. We're not a leaf node, we're not null. And then now if root right is greater than root left data. So 3 is not greater than 6. So we're not going to go into this condition. So the only other thing is times 6 and go to the left. So we're going to have 6. So now we're going to go to the left. Maybe here. And let me just make sure the timer's not going to run out. Okay. So now from this point, we're going to check our conditions. So we can quickly see we don't have a left. So now we're going to go to the right. So now we're going to have 3 times whatever returns from the right. So what we can end up doing is we're going to get up here or down here. And then now we're going to see we're a leaf. So we're just going to return 2. So this call is going to return 2. And since we're doing multiplication, 3 times 2 is going to be 6. Then this is going to end up returning to this one, which is going to be 6 times 6. You're just going to end up returning back upwards to the where you call the function, and you're going to get 36 from this example. So how can we mimic that going iteratively? So a way you can mimic that is by doing the following. So we know that the base case is going to be 1 if we're null, right? So our base is going to be 1. So we can start off a value at 1, because think about it. If we're doing multiplication, what's the one value that you can multiply by and not change your answer? It's just going to be 1. So let's do let's just say answer equals 1. So that's going to handle the base case. And now we're going to start at here. And then we're going to check what condition we're at. So we have a left and a right. So now we're going to do is we're going to add on to this. So we're going to change answer to be times 6, because remember, we ended up going root right was not greater than root left, because in this example, root right is 3. 3 is not greater than 6, so now we're going to go towards the left, but we're going to end up doing a times 6. So we can just take 6 and times it by what we currently have as our answer, right? So right now we have 6. And we can move down where we are. So now we're going to move down to here. And okay, I drew this really badly again. Let me move this over. Gotta stop doing that. And now at this point, we're going to see, okay, we don't have a left. So now we're going to go towards the right. So we're going to do 3 times. So that's going to look like, let me just remove this. So that's going to look like 3 times. So we're going to do times 3. And then now we're going to move down. And then this is a leaf node. So we're going to check what is our current. So current is where these dots are at. Now we're going to see, okay, we are currently at a leaf node. So now we're going to do times 2. So we're just going to add on times 2. So we had 1 times 6, and 1 times 6 times 3, which is 18. And then the full thing is 1 times 6 times 3 times 2, which is 36. And notice how we ended up with the same answer in both scenarios. So this was recursive answer, this was iterative. So I hope you guys see like why it'll still work if you keep the base case at 1. Yeah, just 1 is a great starting point. Anything you multiply by is good. So let's start off with the code. So we can just probably start with this. Well, current is not equal null, which that's probably not going to happen, but you know, it's just a decent base case to have. Another way you can also think about it is while the current node does not have a while it's not a root, and then afterwards, or sorry, when it's not a leaf, and then you can multiply it times 2 here, but we'll just keep it this way. So now we're going to have to handle all these cases. So let's just think about these cases. So if root left, I'm just going to copy these. And also we need our answer variable. I'm going to end up doing answer times equals 2 in this case. And then now we're going to end up iterating and going towards roots. Actually, in this case, this is a base case. So in this case, we just break out. Else if we don't have a left, we're going to do answer times equals 3. Then we're going to set current equals, and we're going to go towards the right. So we're just going to set current equals current. That's right. Else if
Couldn't you write return answer for the if it's a leaf?
oh yeah, you can also do that. That's fine.
Okay, okay.
No, let's do that. And actually that does make sense too, because like the tree will always end in a leaf node. So then yeah, then you can just stop there too. So you can also do that. Doesn't matter. So it's also right return answer at the end. But yeah, we're not done with this. So if you don't have a right, you're gonna go answer times equals 4, then current equals current left. And yeah, you guys get the idea at this point. So
Yeah, you treat it like a linked list almost.
exactly, exactly. That's exactly what it is. Because
Mhm.
that's how you're moving. You're only moving in one direction. So yeah,
Yeah.
that's exactly what I meant with like the binary search thing. If you think about it, from the root to the node that you're search, like the value you're searching for in a binary search tree, that path is just like a linked list, if that makes sense.
Yeah. Mhm.
Yeah, exactly. So that path is
So
always
because one of the questions on the last exam had a linked list question, and they went through it recursively, and that's when I like understood that you can
yeah,
treat it both
exactly.
ways.
Okay, so we're gonna go towards the right, and then else The other case is we're just going to do answer times equals 6, and then current equals current left. So it's a lot of copying, but that's pretty much what the answer is. So I hope the explanation made sense on this one. And let's check the answers. Yeah, so it's pretty much the same structure. So they made a temporary result 1. You go to the left. The way they did it was they set temp equal to null, and then that's going to break this loop. But if you're always going to end up at a leaf, so this would always cut it out either way. So that's kind of like what I was thinking of doing, was saying, just putting this condition up here, since the tree always ends in a leaf, and then at the end you could do kind of like return
Oh yeah.
answer times 2, you know. So that's kind of like the way I was going to go with it, but this also works as well. Even though this would never hit, but this would always end it. So yeah, that's this question. All right, so now we're gonna go on to tries. Okay, so give you guys a couple minutes on that one to start. So at 7:30 we'll come back. Let's see who's here.
Yeah, I'm here twice because I have it on my PC and my phone because I'm moving around. So.
Oh, okay, that's fine. That's fine, no problem. Yeah, it's the day after finals, so everyone, it's cool. Everyone left.
Yeah, I'm just trying to get as much review as I can because
Definitely. Okay, so I'm just gonna start off. So you wanted me to explain what a try was? Since you're the only person here, I'll just, tell me what you need.
Oh yeah, absolutely. I don't know what a try is at all.
Okay, so let's say you want to be able to look up words in a quick way. So you can store words in different ways. So you can store a word like, like a 2D array. So you can store it like this, and then each of these is a word. So, shep.
It's like the double pointers almost.
Exactly. So that's exactly what it's going to be. So you can store it like that. You can store it in a linked list, but there's this data structure called a try that allows you to look it up quicker. Because let's think about this. So if you want to look up a word in this, let's say this not sorted. So if it's not sorted, you're going to have at least n words, right? And then every single letter or every single word has its own length of, you can say s. So for you to find a given word, you're going to have to do like O of n times s. Does that make sense?
Yes, very much. Yep.
Yeah. So then you're going to have to do that every time. But the thing is, with a try, it actually turns the runtime of searching for a word to O of just s, which is just the length of the word. So the whole idea behind a try is this is like the main node. So there's always one root node that's like, I like to say, like the mother of all the other children in the tree, right? So you're going to have a 26 letter or 26 size array of pointers, right? So the first one is going to be representative of a letter. So A, B, C. And like I said, it would be 26. So if there's 26, then there's eventually going to be one that's like index 25, which is going to represent Z. So does that make sense?
Yep.
Okay, so let's say you wanted to add a word cat in. So if you wanted to add a word into the try, you would say, okay, is C in, and by the way, this would start off as no. So is there anything at C? No, there's nothing at C. So now what you're going to do, you're going to make a pointer or make a new node of try, add it in, and this is going to represent like C, right? And now after C, you're at, so we're going to have like this. So we've already gone through this index. Now we're going to be at A. So in this thing, since they all start at null, they're all going to be X's, which represents null, right? So now this one represents A, and then the one at the end, again, represents C. So now you're going to say, is index 0 taken? So index 0, there's nothing there. So we're gonna add something in.
Oh, that makes sense. Okay.
Yeah. And then this is gonna represent A. And
So
now we're gonna
it's literally like a dictionary, literally just
exactly.
going
That's exactly
T and
what it
then
is.
back at A again, B, C.
Ye-
Okay.
Yeah. And then eventually we're gonna have T somewhere, and then this one's gonna be null. So you make the node, and now you're gonna end up with the last node representing T. And yeah, again, these are all null. But then a lot of tries, they have this thing, this like variable, this number variable it represents like if it is a word or not. So since you inserted C, A, and T, so you inserted cat, this would be turned off to 0. It doesn't represent a word. A doesn't represent a word. But then T, since that was like the end of the word, you would turn this one on. So this would have a 1. So then you can say, okay, so cat is in the try, because then you can look, oh, do I have a C? Yes. Do I have an A? Yes. Do I have a T? Yes. And this node, it's on. Like the flag is on. So it's 1, meaning we have the word cat in our try. So does that make sense?
Okay, it makes sense. So what I'm a little confused about is, okay, so we stored empty array of 26 elements.
Uh-huh.
Well, yeah, 26 elements, and they're all null, right?
Yeah.
Like pointers, they're null pointers. So then when you're searching for a word, you're passing in just a character like at a time, because, or do you passing a string at a time and then search array 0 or array 1? Like for cat, would
So
it be like,
yeah, I got you. So it would be kind of like so the structure would kind of look like, so you want to search or insert?
I guess we'll do insert then search, I guess, just because it's similar. Well, insert would require searching, right? Or no?
Kind of. You're kind of doing that, but typically there's two ways to do it: recursive, iterative. If you do iterative, you can just search at the start, and if you find it, then you just stop. So
Okay. They want
so
you, are tries typically done with recursion, or are they done iteratively? I know you could do both, but
so yeah, you can do both, but there's a bunch of stuff that recursive is typically better. But on foundation, they'll tell you every now and then to do either iterative or recursive. Most of them are recursive, but there's some here and there. But it's stuff that you can do iterative easily, like inserting.
okay.
So yeah, let's do something like this. So right now we just have the root, the word, and then hold on. K represents like what letter in the word you're at. So
Okay.
at the start, it would start at 0, meaning we would be at letter
Mm-hmm.
C, so cat. So the
Mm-hmm.
whole idea would kind of be, I'm just gonna like, you know what pseudocode is?
Yeah, of course. Mhm.
Yeah, so I'm just gonna like kind of pseudocode it.
That's
So
fine. Yeah, you don't have to. You just write the algorithm, like what's happening. You don't have to really code it. It's fine.
all right. So
Mm-hmm.
another thing.
So you do word K, right?
Huh?
Almost. You
Yeah.
do.
You're gonna do something like that. So word in try. So this is searching, then stop. So this is another base case. And now after you found out that it's not in there, so the whole idea is gonna say for I equals 0 until length,
Mm-hmm.
right? Then now you're gonna end up doing is you're just gonna check if so they also have for this array of 26, it's gonna be oh shoot. Well, the array of 26 is gonna that always happens. So the array of 26 is gonna be called children.
Yeah.
So you can say if try child child word K minus A. So what this means is like whatever the letter is. So this is just going to give you whatever the letter is. So let's say it was B. So this would be like B. So B minus A would give you index 1, if that makes sense.
Okay. Okay. You're doing word K. So and let's use if we use cat as an example there, it would give us 2 or 3.
Yeah, it would give you 2.
2. Okay, so A is 0.
Mm-hmm. Yeah, exactly.
Oh,
So you just
okay.
say like A is letter 1 minus 1 0. So that's it. You have to give it like that. So if
Okay.
so if it's not there, but if it's null, then what you're gonna end up doing is you're gonna make the node. So you're just gonna do try child word K minus A, and you're just gonna set this equal to, like, you're just gonna make a new malloc, a new node, right?
Mm-hmm.
And then the whole idea is after this point, then now you're just gonna do let's see. So you can do try child word of K minus A, and oh sorry, you can do, I didn't make a variable. So let's call this C. So C is going to be where you're currently at. So we're going to start off
Mm-hmm.
at the root, and then we're just going to set C equal to the new node we just made. So now we're going to go down that path.
Yep.
And yeah, you also want to increment, actually, let me see.
So would you increment K?
Oh, wait a minute. Wait, I was thinking about this recursion, but give me 1 second. My bad. I meant to use a I in this one, if that makes sense.
Yeah. Oh, okay. Yeah. Yeah. Okay. It's the for loop. Okay. Yeah.
Yeah, because I was thinking about, I wrote it like recursively at the start, but this is iterative. So yeah, so then you just go down to it, and afterwards, it only depends if you have this flag. Like if you have this flag in here, then what you're gonna end up doing is at the end, your C is gonna be equal to the node at the end. So if you're adding in cat and cat was not there, then your C is gonna be equal to the node representing T in cat. If
Yeah.
that makes sense.
Mm-hmm.
So now you're just gonna do like C word equals on. So this is like it is a word.
Okay. So you're saying flag 1.
Yeah, essentially. Yeah. And another thing for the num words, it just represents like how many things are in the subtree. So for example, let's say this example. So I'm gonna add in green the subtree size. So as we make a node, we're going to increment the subtree by 1, because now we're going to know, okay, we're about to add it in because that word was previously not there. So now once we add this in, under this, we're going to have 1 word. And then here, we're also going to have it 1. Under this, we're going to have 1 word. And then including this under it, there's now going to be 1 word. But let's say we add in another word, cats. So like towards S.
Oh.
Then
Okay,
now this is going to become 2, 2, 2, and then this is just going to be 1. And then
So
now
is it a
this would
total word
always
starting with that
be,
letter?
huh?
Is it the total word starting with that letter?
No, with the prefix. So cat or CA or just C. So there's 2.
Oh.
Yeah, exactly. So if you're looking for the number of words with the prefix cats with an S, then it's just 1.
Mm-hmm.
With cat, it's 2. C is 2. CA is 2.
Yeah.
Yeah. So that's it.
Yeah.
So
That makes sense. Oh, okay. Yeah. Because there's 2 words that have cat
a part of it, yeah.
a part
Prefix,
of it, and then prefix, yeah. But that only works if it's like the word is cat is in order, right? CAT. It wouldn't work if it's
Oh
like
no,
ATC.
yeah. It wouldn't
Okay.
work like that unless you like do some weird stuff. But no.
Okay.
But you're not gonna get a question like that, to be honest. So
All right.
so yeah. Now that you know a decent bit, then let's okay,
Yeah.
well, yeah, I guess just don't look at it, but
Right, I got the answer now. I'm good.
yeah. So write a recursive function that takes in the trie root and a single letter alpha that represents the number of strings in the and returns the number of strings in the trie that contain that letter. You may assume that the letter is a valid lowercase. Okay. You will probably find it enormously helpful to write a helper. So they're gonna allow you to write a helper. Okay. So note that we are not simply counting how many times it is represented in the trie. For example, if we have apple, avocado, and persimmon, the function call for p is because there's apple and then persimmon. So that's one word. And then even though you have a p here, there's only one word which ends at e. Like this flag would be on, but it has a p in it, like that word, if that makes sense.
Yeah, yeah.
So that's like the whole idea behind it.
Yeah, you're not counting how many P's, you're counting how many words that contain P.
Exactly. So think about it like this. So let me draw the example. So it'll make a lot
But
of
you
sense.
couldn't go just down the P node though.
No,
right? Because
no,
Apple
no.
starts with
Exactly. So you're gonna have to go everywhere to see. So in that example, so you have A, P, P. Right? So this is apple. And then I'm just gonna write V for avocado, and then you get the idea. And then we're gonna have persimmon, whatever. And then yeah, you get the idea. So down here. So so P is not a word. So word is word 0, but number of words in the subtree is 1. Does that make sense? Because persimmon is a word, so yeah. And then as for A, it is.
So if there was just to make sure I get it, like if there was persimmon and let's say there was potato, the number of words would be 2 for P. Okay. All right.
Yeah. Oh, by the way, this one right here, it's always 0. You just treat it like a dummy node. Because it's just like holding up the whole thing, if that makes sense. So without this, yeah. So
just for all the first characters.
Exactly. Because without this, then you have nothing, So
okay. So if something there is no, then you know that there's no word that even contains that letter.
Exactly. There's no word that contains any letter if this doesn't exist,
Or I mean, if a certain I guess element in it is no.
Oh yeah. So if this is like Q and this was null, then yeah, there's nothing that starts with Q. Not has a Q, starts with Q.
Oh, starts with Q. Okay, okay. But something can have Q later on. Okay,
yeah,
I see
like
all right.
Yeah.
That makes sense.
Okay, so the number of words past this point is 2. But the thing is, if you think about it a little like differently, whenever you hit a P down a certain path, you've already hit the condition that, oh, I already found something with P. So now at this point, you don't have to check this P or further down here because you found one. You can literally just take num words. And then just, add it up with whatever it is that you're adding up to. So you're going to exploit that. You're just going to go down as far as you have to until you hit a P and then take the sum of this because this will represent everything down here. Yeah. So this will just represent this, and then
so basically, like in the Apple version, when it goes to AP, whatever num words is the number of words that start with AP.
Yeah. Yeah. Exactly. But let's say you had like avocado, like this whole thing. Like let's say I'm just gonna do
avocado available. It could be like
so let's say D, and then we have O. So ultimately, we're gonna end at D and O. Let's say for whatever reason we had a P here, and then his word is 1. Then once you would have to get all the way down to here because none of these are P or wait, yeah, none of these are P's. But then once you get here, even though it's at the end, then you stop because now this number is inclusive of itself. So it'll be this and everything under it if there doesn't have to be. So yeah, that's the whole idea of this.
Okay.
So let's just get to it. So
wait, so if all right, never mind then. I guess so because I was thinking like if you got to AP and there was nothing under that, and AP isn't a word, like so it doesn't count the words above it, it just counts the words at that point that includes that letter from then
Under
on.
it, under it,
Okay.
under it, and including itself. So and anything that has AP. So AP is a prefix of AP. AP is also a prefix of app. AP is also a prefix of apple. But the only ones that are words out of all of these that I just listed is this one.
So in all those letters, A, P, P, L, E, will it have num words equal 1? Then because at
Exactly.
least
Yeah.
one.
So this one will be 1. This one will be 1, 1, and then this one is 1. Let me delete this
Oh.
avocado stuff. But let's say if we delete this, we delete. Okay, we delete this one right here. Okay, yeah, I'm just lagging. I'm streaming and all that stuff. So just
Okay.
just ignore all this stuff right here. So
Mhm.
this one would have numbers 1 because avocado. D would have it also as well. So there's two things. There's is word and number of words. So this is words. This is number of words.
Okay.
But
Okay.
then this is number of words, and then I guess you can. I'll just do left is word, and the right is number of words. So 0, then 0, and then 1. Then this one is A is not a word in this thing, in this example. So 0, but then number of words is 2
Mm-hmm.
because you have apple and then avocado.
Mm-hmm.
And this one is word is 0, but then you have the O and then the N, permison, and then, oh, yeah. And then this is just
So
going to
so
be.
the last letter in a word would be is word as well as
For the most part,
right.
for the most part, sometimes because like if you end up deleting something, so let's say you go down to delete, what would happen is you're gonna go down and decrement, 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 decrement. So now these would just be all zeros in this case, like past this point. So right here, it would be 0, 0, 0, 0. And this would not be a word anymore. So you have 0, 0, 0, 0, 0, 0, 0, 0. But then this one would just change to 1 because you have another one down this way.
Yeah. Mm-hmm.
So that's the whole idea.
Okay.
All right. So if root is null, we're just going to return 0. So there's no words in. And now the classic thing with these tries is, yeah, I'm sorry, but I use X. So
Oh,
you're just
okay.
going to iterate through it. Yeah, I just like using X instead of I. But now we're going to do root and children of X does not equal null. So if it doesn't equal null, we want to go to it. We can also get by with not doing that, but I'm just going to end up doing it either way in this specific example. So we can do if root of children. Actually, let's do like this. So I'm going to take whatever index we're at. So out of A through Z, whatever we're looking at currently in the for loop, if it equals, if this minus, let me see. Actually, no, if the current index equals whatever alpha is minus A, so remember the whole B minus A, C minus A?
Yeah, you have to do minus A, right?
Yeah, on the character. So this is saying if whatever letter we're at is at the same index that the for loop is at, then that's the case where like, let's say a letter is P, right? Then if we're at A and then we're looking down at P from A, then we can just say, oh, it doesn't equal null, if that makes sense. And then from there we can just add that. So if this is the case, let me just write this a little different.
You could just get the num word from there, correct?
Yeah, exactly. So you can just do store a variable answer. Then you can do answer plus equals root children X num words.
Yep.
And otherwise, if you're not at that letter, you're going to want to recurse because then, like if you're not going to that letter, because then you don't know if there's like the letter you're looking for somewhere inside of a different word lower than where you are, if that makes sense.
Mm-hmm.
So now you're just gonna do count letter of strings, roots, children of X, and then alpha. And then at the end, you're just gonna return the answer.
Would it be X plus 1? Oh, where's a for loop? We're in a for loop.
Yeah.
Yeah. All right.
Yeah, so that's it. So I hope that made sense.
No, that does make sense now. Okay. I
Mhm.
was always wondering how to get the ASCII values for, I guess, letters, but you just subtract it from A and that will give you the.
Yeah, so this is for lower. This is assuming it's lowercase. So it says I don't even know if it
Yeah,
says lowercase, but
it's,
yeah,
it
valid
says that.
lowercase. By the way, like lowercase or uppercase A starts at 65 and runs to 90. So it's like 65 to 90, and then lowercase goes like from 97 to 122. So this would be like your Z, and this would be your big Z right here. So
Oh, okay.
yeah, but you don't have to know these numbers. You can just use like this, and that's good enough. It'll calculate
All
it.
right. Okay. All right. That makes sense. Yeah.
So let's take a look. Okay, wait, I gotta zoom out on the PDF here. All right. So you iterate through all 26. Then if I equals alpha, yep, that's good. Alpha minus A. If it does not equal null. So they just did like this a little different order. And root plus equals the num words. So you just stop there. And once, if that's not the case, if you're not at that one, then just add whatever else you find deeper in the try and then return the answer.
Mm-hmm.
So yeah, that's it.
And you check always if it's not equal no first, right? Because if it's no, you're just going to skip over anyways and go to the next
Exactly. The only
letter.
reason that they did it here was because they use the base case. Like in this example, they don't say that the try will in it, like the very top one, the one that I said was like a dummy one that holds it all
Mhm.
up. They don't really check if that one is, they don't say that it can be null. So that's why like they're just doing plus equals and they're not checking if it's null here, because if it is null, then you're just gonna return 0. So like that's kind of like why
Yeah.
they're, but the only reason they're doing it here because they're arrowing into it. And then if
Mhm.
they arrow into a null, then you can seg fault.
Yep.
So yeah, that's the whole idea. So yeah, let's go on to the next one.
All right. That made tries a little bit more understandable for sure.
Mhm.
So here, I guess, you go down every string and see which string has the highest number of words associated.
This was a little different. They don't give you the num words. So they give you a flag, but if you think about it, the flag kind of represents the num words as you go
Yeah.
back up the recursion. So you would kind of
Yeah.
use that to to go get your answer.
So would it be the longest row of flags that are 1 or no?
That would be the answer, yeah. So it's gonna be like, I guess you can say from any leaf node. So like you know how like binary tree, the leaf node just has no children.
Mm-hmm.
So in a try, it's just like there's none of the 26, they're all null. So it's
Mm-hmm.
like kind of like the longest path, or I guess not necessarily the longest one, but the path in the try that has the most ones in it, like in terms of
Yeah.
like flag zone. Yeah, exactly.
So while don't so I mean not while, but you if I guess you check the flag of the current node you're in. If it is 1, then continue on to the next, or just start from that, make that the root, and then traverse that. It's
I see what you're
letter.
saying.
So,
The only thing is that like if the flag is off, then like what are you gonna do in that case?
oh, like if flag is 0.
Yeah.
then continue to the next letter in that root itself. Well, I guess
Mm-hmm.
I would
Yeah,
check.
you're on the right track. You're on the right track. So let's go up with the same kind of idea. So let's see. Okay, that's not a square. Okay, so let's do A, P, P, apps. So I'm just gonna do the flags. So this is gonna be 1, 1, and let's see what else. Let's say this is 1 here. Actually, let's say this is 0. So we have apps, and then I don't know. I'll just use X for whatever reason. Then 1, 1. So let's call this Y and then Z. Now to C, A. Okay, so now in this whole try, what do you think is gonna be the wait, let me just finish this up actually. So what do you think the maximum prefix is gonna be?
In this tree.
Yeah.
So we go down A 0, then we C, B, D, then P 0. Oh well, it only has P. Well, oh, it has P. Well, P 0, so you go to P, and then check A, B, C, you go to P again, and then check A, B, C, S. Okay. So let me start at C now. So it'd be 1, 2, 3, 4, 5. Would it be from C, U, D, D, D?
Yeah, yep, that's it. So the way that you can come up with that is so let's do this maybe white. Let me do it in a different color. What's up?
So can I tell you what I thought and maybe see if
Yeah,
that makes sense? Okay, so I thought, okay, we start at root, right, which is A through Z, right? We'll assume, and then we start at A. We see that A is available, and then we start again from you start from that node, you go from A, B, C, and then you get to P. See P is available, get to P, start again, A, B, C, you get to P again, P is available, start again, get to S, S is available, start again, the rest is no. Then you'll store how many, I guess you'll return, I guess the height of that back
What
to
do you mean like the flag or the height? What do you mean?
oh well, if you'll return, I guess the flag, if it's, I guess if it's, because you need to keep track of the height or how long the flags are though, even though, right, because
Not necessarily the height, because you can have like you can have one word with like let's say length 40, but then there's only one thing in like one word in it, if that makes sense. Like
so
you
how
can
would
have you can have
how would
something
you
like this
return,
gigantic, and then it's only one thing, you know. So
but
length doesn't matter.
okay, so would you say something like if it doesn't have children, so if I don't know, because you drew it like a binary tree, so I was gonna say if left is if, well, you can't do that, no, because you still
Yeah,
have
you
to check
can.
every node. Okay, so all right, I'm not too sure how to code it, but I kind of thought about it. I just don't know how to return. Because if you go to C, C is available, then you go A, B, C, you check A is only one, and then there's nothing after A, and that's only one like flag in there. Whereas if you go C and you go all the way, you find U, and then you start at A, B, C, D, D's available, then again, D's available, then D's available, and that's longer than A, P, P, S. So you return that side, but I just don't know how to keep track of that length and how you.
So you're kind of on the right track, but you're thinking about it a little wrong. So
Okay,
it's saying maximum number of prefix words. So the example that they give you, let's see. So they say intention has 4 prefixes: I, in, intent, and intention. So the one with the maximum prefix, so I is a prefix of in, right? It's also a prefix of intent, and it's also a prefix of intention. So the maximum, let me see. Wait, what's the prefix of words that are prefixes? Okay, so you're trying to count the number of prefixes of a given word. So a given word could be intention, and there's
they give you a word. Okay. Oh.
Wait, no, they don't give you a word. It is just an example. It has 4 prefixes, and a word can be a prefix of itself. So the whole idea is it's kind of like trying to calculate the num words field in a way where instead of like incrementing it as you go down, what they're doing is you go down, but then you take the maximum of all your children. So for example, right here, you're going to take the maximum of what you get. So it's just going to be 0 because there's nothing under it. And then you're going to add this to whatever the flag is, if that makes sense. So the flag is going to be 0 plus 1. So now you're going to end up returning 1 back up here. When you return 1 up here, you're going to see like the maximum you get from your child is 1 because that's the only way. All the other ones are going to be like 0, 0, 0, just 1.
Yeah.
So now you're going to get 1 plus is it a word or not? So now you're going to see that for instead of thinking of like prefixes, I guess you can think of it like how can I explain it? Just give me 1 sec.
Okay. So would P be 2 now, and 2 returns into the P above it, and that'd be still 2 because there's no well, I don't know.
So I guess the way you can think about it is you're trying to calculate how many prefixes are in a word. So intention, you're going all the way to the end. So let's say this is in the word intention, but it's apps, right? So you're gonna go all the way to the end, and you see intention is on. So the end is on. Then you're gonna go back, and you're gonna end up seeing intent. That one's gonna be on. And then as you go back up, so it's kind of like instead of thinking of prefix on this one, it's kind of like you're thinking about a suffix, if that makes sense. So you're like saying, okay, is there like instead of thinking prefix like this, it's more like, okay, so from the end, like this ends in a word, then this ends in a word right here. So we have 1 and then 1, so we have a total of 2. And now as you go backwards, this is not a word. And let's see, A is also not a word. So like the best you get from just this example right here is 2. Because this would be 0 and 0, but you added these 2. And 1, like this 1 right here, like PS, it also contains another 1 inside. So that's why I ended up doing 1 plus 1 equals 2. If that makes sense. So like you're kind of going backwards, and that way, since you went this way, you can see how many words end up making up, like how many prefixes a given word apps end up having, because you're going from the back. If that makes sense.
Yeah.
Yes. So like you're going backwards. So as you come back up, you're going to take the maximum that you calculated from your children, like the recursive calls from the children, and then you're going to end up adding whether or not it's a word. So then you're going to say, okay, the best I got was 1 plus 1. I'm going to end up returning 2 because you got 1 from here, then 2. And you end up going this way. You're going to end up going this way. You get 0, 0 plus 1. You're going to end up returning 1. Go down this way. 0 plus 1. You're going to end up returning 1. So you're going to have 1 and 1. The maximum is going to be 0 or 1. And now you're going to add 1 plus 0. And that's going to end up returning 1. So now at this point, you're going to say, okay, what is the best of the 2? So I get 2 plus whatever it is here. So it's just going to end up returning 2 and so on. So now you know at this point, hold on. At this point, the best I've done by going down this path, like this entire segment right here, is apps. Because like going down to apps, I know that I currently, up until P, I have two suffixes that are
Yep.
ending, like, they're like create a word. So yeah, then you're gonna end up doing the same thing. So you're gonna end up returning two.
So couldn't a node have more than two paths then?
What do you mean a node?
Because like, all right, so P goes down to the left as like PS, and then to the right is X. But couldn't like there be a?
It can have 26 up to 26.
Yeah. Okay.
So you would just
all of them.
Yeah, you would have to take max throughout all of them. So in your for loop, you would just have to take max and max and max and so on. So yeah, let me just run through this real quick so you can see what I mean.
Mm-hmm.
Oh wait, I meant 2, and then
3, and then to the right of that is.
Oh wait, this is a Z. My bad. It's a Z.
Oh, you're all good.
And then this is a 1. So then you're gonna get 0, 1, and then let's
compare
just
3 and 1.
3 and 1. You're gonna take 3. So 3 is gonna end up going. Oh yeah, and you're also adding if this is a word or not. So 0, 3 plus 0. Then now at this point 1 and 3. So take 3 plus 0, which is 3. Then in this side you're gonna get 2 and 3. So max of 2, 3 is just gonna be 3.
This is like pre-order traversal, right? Almost.
I wouldn't say post, honestly, because you're going all the way down, and then as you come back up
and
is
then
when
come
you're.
back up.
Yeah.
Yeah. True.
So yeah, you're kind of doing that on this, but yeah, it's all based on the suffixes, kind of. So this and then
Okay.
yeah. It's interesting because you're thinking about it a little differently. Instead of usually the problems follow prefix, not suffix, but that's kind of like the idea in this one. That's the way I think about it. So base case always here's null change 0. So you have the maximum, and you're just going to iterate through all of the children. And let me see, how can I do this? Yeah, in this one, I'm just going to do, I'm not going to check if root is null because I'll just recurse there. And we're not like the last one, we were arrowing into null words. But in this one, we're not going to end up doing that. So I'm just going to do like this without the if does not equal null. So I'm going to do maximum, let's say sub answer from recursion. So we're going to say maximum numbers root children of X. And now we're going to take the maximum. So if sub answer is greater than maximum. So if going down a given child is better than going down a previous child, like one that we went before. So like, let's say we found from A, we found 3, but then going through Z, we found like 20. Then in that case, we're gonna take 20 instead of 3. And that's about it for the for loop. And now at this point is where we're gonna say, okay, let's take the maximum, and then let's account for whether or not we are where we are right now. So I hope that makes sense.
Yeah. So yeah, it's could you run through the code just like one last time?
Like
from the for loop. Yeah.
So iterate over all 26 children. This is gonna store like going down a given child, what answer we get from the recursion. And if that answer, like let's say going down B, we find 5 words. And so we started off at 0, and then B had 5, or actually let's start at A. So let's say A had 2. Then the maximum of A and 2, or 2 and 0 is going to be 2. Then let's say at B we found 5, it's going to be maximum of 5 and 2, it's going to be 5. And if we found at index 25, which is Z, if at Z we found like 40 words, then we're going to end up taking 40 instead of 5, which was the previous maximum. So as we go down a given path, so it's just like in this example, we got 2 from this side, so our maximum was 2, but then when we ended up going to C, we found a better maximum of 3 at the end. So then we came back up and we were like, okay, our maximum is currently 2. Let's compare that against 3. 3 is bigger than 2, so now 3 is now our maximum.
Okay.
So that makes sense?
Yeah, it's starting to make a little bit more sense. I just didn't know where, because I was thinking about like, because in sub answer, you're pretty much going to check all the characters, but where are you saving the oh, you're saying return maximum plus root flag there. Okay.
So that's kind of like get the maximum of all my children and then add whether or not I'm a word.
Okay.
So that's how you get like the suffix kind of behavior where you're like everything under me, the best thing under me, plus if I'm a word, then keep going. And that's going to be the best up until that point, coming down from, wherever the letter was in the array. So that's the whole idea.
Okay.
Yeah, this is one of the more confusing ones that people generally have trouble with. Oh yeah, let's do like 1, 2 more.
So for something like this, would you, so like, let's say the string passed in was like Apple, like, would you then go to use a root? And it has to be iteratively, so you do a for loop, I guess. Maybe I guess it's all lowercase characters. So would you still do 26, or would you?
No, it would always be 26.
Yeah,
it doesn't matter
so
if it's lowercase or uppercase.
Okay, so if you do like a for loop and then you check, if I guess you'd have to iterate through the string passed in and the root, but like, because if the word's apple and the first node or first element in the root is A, then you would see if flag is there, I guess, to see if that is already part of a word. If it is, you would have to, because that's what the only thing I'm confused at what flag, I guess, means for here, because like if flag's on at A and the string pattern is apple, does that mean that there's an A node already created, or you'd have to?
Well, I mean, for the flag to be on, that would mean that it would have to be malloc. So if it's
so it can't be null. Okay.
Exactly.
So you have to look for. I guess then you would say, okay. So I guess you would have to check each node that or each element that represents a letter in the string passed in and check that it's not null. Like if it's null, then you'd have to create a new node there.
Yeah, and then you would just have to return like whatever number,
Yeah. So
Exactly.
Okay. So you just find the amount of, I guess. So if apple's there, you go to A, see if it's null. If it isn't null, then that's one needed created, add one, and then I keep going through.
Exactly. So yeah, exactly. So I'm not gonna explain this one. I'll just go through it and explain it as I go because you have the general idea.
Yeah.
So you must handle the case where root is null, they say. So root equals null, return 0. Okay? And then now we're gonna have to make our for loop. So the way I'm gonna do this one is I'm gonna do I'm not gonna do a for, I'm gonna do a while. You can do a for as well, but I'm gonna do a while. It'll be a little differently. Actually, let me see. Yeah, I'll just do it. So I'm gonna set a temp variable. So I'll just call it so current equals root. So that's gonna be where we're gonna start off at. Right? Or actually, my bad. This right here, if root is null, then we're gonna want to
+1.
Wait, no. They say, yeah, you would have to do. I was about to see if you would catch it. Yeah, you would have to do +1, but they say only try to calculate it once, and we might have to calculate it again. So what I'm gonna do is I'm gonna say.
Wait, what do you mean calculate one?
Like string length, the string length, because like think about it. If root is null, you would have to
Oh.
create nodes for every single letter plus the main root that holds it all up.
Oh, okay.
Yeah, and then like for the case where it's not null, then I would have to do string length minus whatever letters I found, you know. So
Mm-hmm.
that's what I'm gonna do. Length of string up front. And now what you can do here is you can just return length plus 1. That's in the case that there's nothing there, like there's literally nothing, it's just null. So now what I'm going to do is I'm going to also create another variable. So this is going to be like representative of how many letters we found, and it's also going to iterate through the word itself. So the whole idea is going to go while current is not equal null. So while we haven't hit a null node, right? And then now another thing is x is less than the length, because then once we hit the length, we know that we're like we found the full word. If that makes sense.
You're
And
gonna increment
now
x every time you find
exactly,
you're
exactly.
just increment x at the end and just go through the whole length of the word.
Right. So current
So when you say,
equals
just to make sure I understand, when you say return length plus 1, you're saying that that's the amount of new nodes needed, although that the length of the actual word.
yeah. So let's say apple. Apple is 5 letters, right? So that's 5 nodes. But if we don't have a main root, then we have to add that one as well.
Oh, I thought that was for the node. Okay, so
To
that's
hold
for
up the whole thing, yeah. Oh no, it's not for the null, it's for the main, like the dummy node at the top.
Okay.
So current children of, and we're gonna take whatever the word is, so string of x minus a. So does that make sense why we're doing that? We're taking whatever letter, okay, an x plus plus. But there's actually, let me see. There was a weird case with this where, let me just make sure of something.
You're just using current to compare, because you're using the numbers, the ASCII number system to compare the string. It's the actual character itself. Is that why you're saying
Exactly,
current?
yeah, exactly. So let me just think about something. So yeah. So after this condition, you cannot just keep going like this, because there's one weird edge case where you'll actually be off by 1. So let me just explain why that is. So let's say you want to add an apple, right? So let's say what you have right now is a so yeah, so let's say you want to add an apple. So we're going to start off right here, right? And our x is going to be 0. And now we're going to go towards A, and we're going to say, okay, we're good. We're good at A. So C is going to be here. X is going to be at 1. Then we're going to go towards P. So C is going to be here. X is going to be equal to 2. Now we're going to move down. C is here. Then X is equal to 3. So now the way that our code works is we're going to move C, and then we're going to increment first, and then we're going to check if we're done with the while loop. So what's going to happen actually is we're going to go into the index of L. So we're going to go to L, right? So the thing is, L is not there, right? So it's just going to be null. So really what's going to end up happening is we're going to have C at null.
Just 3.
Wait, actually, no. So this is a weird thing. Okay, shoot. Well, hope you didn't see it. So
no.
let's say C is equal to null, right? So if C is equal to null, the way we have our code right now, we're moving C and incrementing. But the thing is, our increment tracks how many letters we found so far. So even though C is null, we're going to end up incrementing, and that'll make it seem like we found 4 words of 5, but really we only found 3 words of 5. So you see like the weird case?
Yep.
So what you're going to have to do is before you increment x, you're just going to check if after moving current down, if it equals null, then you can just break. Actually, you can also return, but I'll just do break. So it's just going to stop here, because if not, then we're going to account for a letter that we actually don't have, if that makes sense.
Yeah. Yeah.
And now at the end, we're just going to return length minus x, because now we're going to have, let me go back to the whiteboard. So if we have apple, so 5.
Okay, yeah. That's how many
5
numbers
minus
we
3
need.
equals 2 versus 5 minus 4 equals 1. So yeah,
Yeah.
that's like a weird little case on that one. But yeah, that's how you would end up doing it.
Yep.
So you found 3, and then that's it. So yeah, I hope that makes sense.
So what couldn't you have done? Can you go back to the code real quick? So wouldn't the while loop not run though if current is null at the time?
The thing
right?
is,
because
we're moving it down in here. So this
in there, yes, we're already in
exactly
the while loop.
yeah.
Okay.
So if we don't do this, we might move it down, account for a letter that's actually not there, and then after we process these 2 lines, then it would cut it off if it is null, but we would have already accounted for it, so
yeah,
that's why.
Mm-hmm.
And that gives us the answer.
Yep.
Yeah, so they did it. They pretty much didn't set up the break. They just stopped it here. So same exact thing.
Yeah, they did it with the for loop there. That way they yeah. Mm-hmm.
I just wanted to like handle multiple, but I guess this is kind of redundant. So you could have done it with the for loop as well, but this also works too, So yeah, different ways.
Mm-hmm.
But yeah, same.
An array of characters or no?
Hashes are what? Sorry?
Are hashes similar to tries in that they work of an array of characters or no?
An array of characters.
Like you know how in tries we had our root which had a.
Oh, I see what you mean. Well, they could, but not really. Normally, you're just dealing with a numerical value, and then you're doing something to it. So the general formula for when you're doing hash tables is going to be hash value mod table length, and then whatever answer this is, that's where you're going to try to place something. So there's different types of probing. So it's like quadratic probing and linear probing. So linear is literally like linear is like if this is taken, it's just gonna add 1 until it definitely finds like a place that's empty. Quadratic is where you're gonna let's say you want to add to 1, right? So it's gonna go C1, let's say 1 is taken, right? So now you're gonna start and you're gonna see, okay, 1 is taken. Let me do the location of 1, so 1 plus, and then you're going to have a number. So it's going to be like, you can call it Q1. So initially it starts at 0. You're going to check is the value. So this value here, let me just calculate. So this is for a quadratic. So hash value mod table length. Let's say this equals 1, but 1 is taken, right? So now what you're going to do, you're going to increment Q up, and now you're going to take this value, so this location of 1, and do 1 plus Q times Q. And then that's going to be 1 plus 1, which equals 2. And if, let's say, 2 is not taken, you would place it at 2. But let's say 2 was taken. So if 2 is taken, then you're going to set Q equals to 2. And then now, and this is not tied to whatever the value this is. This is just like a for loop. So this could just as easily be like a 6. This could also be like a different number. This could be like a 5. So it would just change like this, for example. So let's say 6 is taken after trying. Then you would set this to 2. And then from there you would do 6 plus 2 squared, which equals 10. And if 10 is not taken, you place it there. And then if not, you just go Q3 and then you keep going endlessly until, you're good. if that makes sense.
Oh, okay. Okay.
Yeah, and also always remember to mod this by table length, because if you go past the table length, like for example, let's say the table length is like, I don't know, 11. So if you do 10 mod 11, you'll just get 10. But let's say your table length is 11, then when you do the original location, it was like 1,
Mm-hmm.
then
So mod
times,
it and then turn it
yeah,
to something
yeah,
less
and then you
than
would have to
10.
like wrap back around.
Yeah, it keeps numbers less than 10 essentially, right? Or like,
Exactly.
yeah.
Yeah, whatever the value is. So that's the whole idea. So in this one, quadratic probing, let's just let me just take a screenshot of it and get it on my whiteboard. So okay, so let's see for the first value. So we're gonna insert wicked, which is 359, right? So when you do mod 10, so the table size is mod 10. So you're gonna take the hash value mod 10, right? And 9 mod 10, so it ends with 9, so you're just going to take 9. There's nothing at 9, so now you're going to put wicked
Oh, you
here.
take the last value and just mount that by 10? Is that what
No, no,
happened?
no. I'm saying when you do mod 10, it's just the last number, always.
Oh, okay.
Because whenever you mod, it's going to be 0. It's going to be the range from 0 inclusive to the mod value minus 1. So this is going to be in the range of 0 to 10 minus 1.
Oh, it's 10. Okay, that's
Yeah, so it'll give you
okay.
whatever that number is.
So that's what. Okay, yeah.
So you're gonna add wicked in here because it's not taken. Then cheesy, take the 2. If it was like 11 or 12, then you gotta think about it more, do some more math. But it's 10, so just take the 2. So you're gonna put cheesy. Then 1 for lasagna.
Okay, so the whole word goes in the spot. Okay.
Yeah.
All right. All right.
And now we're gonna do 4, 9. So it's taken at 9. So now we're gonna take the location of whatever, like the value mod. So the value mod, the table size 10. So we're gonna take, this is 4, so it ends in 9. So 9. And now what we're gonna do, we're gonna add start queue off at 1 because it's taken right now. So now we're gonna do plus 1 times 1 mod the table size, which is 10. So now it's gonna be 9 plus 1, 10. 10 mod 10 is just 0.
1. Oh, 0.
No,
0
yeah, 0, because 10 goes into 10 once.
remainder.
Perfectly, yeah. So now we're gonna go to 0, and 0 is not taken. So now we're just gonna place 4 here, and then now we're gonna do dinner. So dinner ends in 9. So wicked is taken. So we can just look at what we previously calculated. So this ended up. So this is gonna make it quicker, but you would end up seeing, oh, 9 is taken. So now you're gonna have to do this same step as well, like for
Yeah, 0 is already taken.
Yeah, 0 is taken. So now you're just gonna do
2 times 2.
9 plus 2 times 2. And then you gotta mod this whole thing by 10. So 9 plus 4
3.
is 13. So yeah, it's just gonna be 3. And 3 is not taken, so dinner.
And it always goes up by 1, right? So if 3 was taken, we would have did 3 times 3.
Yeah, exactly.
Or okay.
And that's that. And if it was linear, if this one was taken, just test this one. If this one was taken,
1,
this
2,
one,
3.
this one, and then come back around and so on.
Okay.
So linear is very easy. This one is a little trickier, but you always have to remember wherever the first collision started, that's the number that's going to stay constant. The only thing that changes is the factor that you're adding, multiplying by.
Hold on, let me screenshot this real quick. Okay, awesome.
So yeah, that's like literally pretty much all it is for what do you call it? The hashing for linear and quadratic. When you're doing the linked list one, all it is you have an array, right? And then whatever value it gives you, instead of dealing with collisions like jumping around like quadratic and linear, what it's going to do is it's just going to add it to the start of a linked list. So let's say you have a linked list here, and then you add here, oh, there's already something there. Like this is already there. So what you're gonna do is gonna make a new node. So you're gonna make a new node, and then you're gonna point that new node to what was previously there, and that's it. If that makes
Okay.
sense. So let's say this is like location 0. So you did like 390 mod 10. You're gonna end up with 0. Let's say you had hi, and then you had hello for whatever reason here. Then if the word you were gonna add was like hey, and now you would make hey, instead of this pointing to this, you would point this to this one, and then this one to this one. And
Oh, okay.
so
All right.
that's
It
like
doesn't
how
have
a
to be in like
stack works. A linked list stacks pretty much.
okay. So it doesn't have to be in like alphabetical order or anything. It's just it has to be
Just
stuff like
add
that.
it
Okay.
pretty much, yeah.
Okay.
So that's pretty much it for like hashing. Let me see. Yeah, so let's see the answer. 4 lasagna, cheesy dinner, wicked.
Nice.
And I'll do one more, and then I guess just call it a
Yep.
day.
That's cool. I'll have this and rewatch this stuff later too.
Yeah, I don't see. Okay.
I saw separate chaining. I have no idea what that means.
Separate chaining is a linked listing I just told you. That's all it is.
That's what that means. Oh, okay.
That's all it is, yeah. So let's just go through this one real quick.
Mhm.
So this one is take the number and mod it by 10. Okay, so let me also screenshot this one as well. Okay, so the way this will work is same type of way. So it's mod 10. So 4, it's going to place this in here. And we're doing quadratic, by the way. So we're going to see 4 again. So now we're going to take the original location, 4 plus 1 times 1. That's 5. Oh, yeah, you also mod this by 10, but it stays the same number. So 5 is not taken, 344. Mod 10, 3 is not taken. So 483. Then 4 is taken. So now we're going to do 4 plus
1 times 1.
Yeah,
4
so it's
plus
going to
1
be
plus
4 plus 1 plus 1. So we're going to end up here, but then now we know we're going to go 2. So 2 times 2, mod 10. So it's just going to be 8.
Mhm.
Then we're going to go to 8. 8 is free, so 564. And now we're going to skip all this work because we know, so
Yep.
4
Oh, that's
plus.
pretty simple.
Yeah, so now you're just going to try 3 times 3. Mod 10. And this is going to be 9 plus 4, which is going to be 3 or 13. Mod 10 is 3. But the thing is 3 is taken. So now you're going to have to go again. So that's pretty much like how it all is.
Yep.
So now let's go again. So we're going to do so it's going to be 4 times 4, 16 plus 4, 20. 20 mod 10 is 0, and 0 is not taken. So that's it. So that's all this question is.
All right. Those aren't the worst. Okay.
Yeah. So 8, 14, 43, 234. So let's see. Yep, exactly. So that's about it for hash table, to be honest.
Okay.